So I guess the streaming works right now, right? Are we live? Yay, we are live. That's great. Yeah, Alexei is holding, nice, doing everything in the background to actually make the streaming work. So it works. Yay. Great. Just on time. Thank you. So yeah, you can share the streaming link. Actually, let's put the streaming link here. You can share the streaming link in case your colleagues are not registered to ICCV. Maybe they want to see the keynotes, etc. Oh, sorry, not direct message. Everyone in the meeting. Streaming, yes, great. Okay, now we can start. So thanks everyone again for coming to Deep Learning for Geometric Computing workshop. This year in ICCV, we are organizing the third version with a really good organizing team. So just to give a background about why we are doing that. By the way, can someone confirm that you are seeing my screen? Just to hear another human voice. Okay.
Yes.
Okay, thank you. So just to give a background about the problem, right? So the machine learning methods dominate the computer vision field, and public data sets and benchmarks have started to play an important role for relative scalability and reliability of different approaches. So we have seen like classic tasks on shapes are advancing, but what about like global shape understanding, more parameterized representations and hierarchical decompositions, right? So this workshop, Deep Learning for Geometric Computing workshop, focuses on geometric deep learning for shape understanding, and we aim to bring together researchers with different perspectives by releasing public data sets and baselines such as Skeleton and ABC data sets and challenges, then creating global challenges as the dataset and challenges to benchmark different approaches, and then organizing a workshop to spark new collaborations and ideas. About the collaborations, we will actually talk a little bit more later. So we have an amazing team of organizers, as you see here, some of which are right now online. Some of them will be online throughout our workshop. And we also have a nice team of, sorry, just trying something. On the Zoom, I'm really sorry. Okay, sorry, okay. So we have a really nice team of researchers, all the way from professors to grad students that help us with reviewing the papers as the program committee, or help us with the technical challenges, etc. This team has been changing from year to year, but I thank everyone who has spent some time on Skeleton or for reviewing papers. So, as I keep saying, Skeleton or the Skeleton. So Skeleton is has 4 tracks. It is the dataset and challenges. So the first track of Skeleton is pixel Skeleton, where we define the problem as binary shapes to extract binary skeletons from binary shapes. The second one is point Skeleton, which we are trying to extract point skeletons from point clouds. The third one is parametric skeleton, which we try to extract parametric skeletons, which are defined by Bezier curves from binary shapes. And the last one, which we added recently in the last CVPR, or a little bit before that maybe, is the skeleton extraction from natural images. So I'm skipping, I'm like just giving the names of the tracks, but we will have challenge talks during the workshop where you can get more information about the challenges and the data sets. We also have 3D data set, which is the ABC data set, which has 3 tracks in this one, which is shape segmentation. The first one is shape segmentation, where we have point clouds and feature lines. And the problem is learning towards learning general shape parameterization by robust shape descriptors. The second one is sharpness field extraction, again from point clouds and distance of feature lines, and where we can do planarity and curvature estimation. The third one is surface normal estimation, where point clouds and point normals are the subject to be found. So workshop papers, we have many papers this year. We have 3 oral presentations, which are skeleton net, advanced net challenge attention blocks for skeleton extraction, towards efficient point cloud graph neural networks through architectural simplification, and investigating transformers in the decomposition of polygonal shapes as point collections. You will see all of these papers, oral presentations in the workshop program. And thanks again for all the reviewers and last-minute reviewers for the workshop. We also have spotlight presentations that you can see in the program. And if you look at the program, we will start with the keynote of Niloy. He is also here waiting. Then we will have an oral presentation. Then we will have a small break, and we will go with the spotlight presentations, where it is approximately 5 minutes each, then a Q&A session of 2 minutes each. Then we will give more information about the challenges. Then we will have the lunch break. Then we will have another keynote, another oral presentation, then another keynote, then coffee break, then another presentation, then award ceremony. So let's go to the keynotes. The first keynote will be from Niloy Mitra about neural surface maps. The second keynote will be from Angju Kanazawa about real-time rendering of nerves with planar trees. The third one will be from Justin Solomon, geometry processing inspired deep learning. And I'm super looking forward to all of those keynotes. They are super interesting and like the state of the art. You cannot find novel things than those, right? So thanks again for all our keynote presenters for choosing our workshop to give their keynotes, basically. And lastly, award ceremony and collaboration session. So this year we actually have some best paper awards. The best paper award categories will be the best paper, the best student paper, and the best challenge paper. And the recipients will be announced live in the award ceremony. So I suggest all authors to be there if you think that you are actually a best paper award candidate. So see you in that session. And following the award ceremony, we will have an open collaboration and discussion session with everyone. Like we invite everyone, like all the keynotes, all the authors, all the poster presenters, all the organizers. So we will have this open collaboration session to see new research directions and see how we can actually improve upon like both the challenge and data sets, but also in the general theme of geometric deep learning. You know the links. I try to shout the links everywhere. Like if you go to Skeleton, Pixel Point, Parametric, and Object, or if you go to Bitly, ABC, Shape, Sharp, Normal, you will see the challenges and data sets. So check them out. We are doing streaming. This is not the streaming link, but use the streaming link in the chat. I'm really sorry. And use the hashtags DLGC, ABC Challenge, Skeleton, and ICCV 2021. Of course, I'm sorry about that. So without further ado, I'm leaving the mic to Geraldine to introduce Niloy. Thanks, everyone.
Hi. Thank you. Thank you, Ilke, for the introduction. And it's a real pleasure to introduce the first keynote speaker with Niloy Mitra. So you probably all, if you are here and interested in geometric deep learning, you probably know Niloy Mitra. He has been doing his undergrad in India and did a master and PhD in Stanford. And then he was a postdoc in Vienna and hold academic positions in Delhi, KAUST, and finally in University College London, where he became a professor in 2014. He has been awarded European Research Council starting grant on smart geometry. And he has also been awarded ACMC Graph New Researcher Award for its outstanding work in discovery and use of structure and function in 3D objects. In 2015, BCS Roger Needham Award and also a Eurographic Technical Contribution Award in 2019. So he has been giving a lot of keynotes also, starting in 2009 already. And if I counted well, he has been doing like 20 keynotes. So we are the 21st in 2021. So that's really nice. And I remember his keynotes in curve and surfaces in 2010, which was very nice, and on symmetry in 3D object. And he also gave, he had part of his research where he mentioned and where he was inspired by this great book you may have read, The Way Things Work, which is a child book on structure and how geometry come together and make things work. So I think he has been making our field very exciting, and I really look forward, like all of you, to hear what we can learn from him today again. Thank you.
Let me just share the screen. Let me see if it works. Can you see my screen?
Yes.
Yeah, and you can hear me okay, right? Thanks, Geraldine, for the introduction. It's amazing that you remember me from the talk at Avignon, I believe, from curves and surfaces. And the book you referred to, I was looking next to me. It's still on my bookshelf here. It's one of the few books that I refer to sometimes. So welcome, everyone. Good afternoon, good morning, or good evening, depending on which time zone you are in. And it's really a pleasure to give this talk at this workshop on deep learning for geometric computing. And I'm going to talk about neural surface representations. And I would elaborate what I mean by that. And I think it's going to be a central thing moving forward. And I will explain why I think it's important to work on this problem. So I'm Niloy Mitra. I'm a professor at University College London, and I also head the research group in Adobe in London. So as we know for the audience here, that 3D objects, we all love 3D objects, right? So these are meshes of certain form, point clouds, distance fields, etc., with appearance on top, right? That can be rendered, that can be captured, interacted, right? So when we talk about deep learning, a central question is, in which representation should we have this? So what is a suitable representation that allows us to differentiate, because that's why deep learning architectures are so powerful, both the geometry, which is the easy part, as you will see, because this is a continuous change, but also the topology, how things are connected. And this is the discontinuous part. And that's what makes the whole problem so challenging and in certain sense so exciting to work in. Now, over the last few decades, triangle mesh is now established as the ubiquitous choice for 3D surfaces. Although we work on other representations, but triangle meshes continue to be the dominant form given its simplicity and given how well it's integrated with all existing workflows. So hence we want to, we really love this data structure, we love this simplicity, and we would love to operate on this representation. The problem is, it's not differentiable. Now, in certain sense, it is differentiable if we keep the connectivity fixed, or the triangles fixed, but move the vertices. But what we really want to go is beyond that and also change the triangulation as we move. And that's our main idea today, main agenda today. Just as a quick recap of last few decades of work, how people have worked around this problem. One is we kept the connectivity fixed, right? So we kept the connectivity fixed and worked with moving the vertices around. Very good. The second approach is we try to remesh the object after deformation. So this can be a local remeshing, or in a very extreme case, we remesh from scratch. But again, this is a very discontinuous operation. Now, in the paradigm of deep learning, where we want end-to-end differentiability, this is not compatible. Right? If we look at our image domain, where operations can directly be defined on the images directly, we have seen that we can benefit from the accelerations provided by GPU and the robust differentiation modules we have. So the goal or agenda for today is, can we reach there with our favorite data structures? This brings me to the topic of neural surface representations. So the first thing I will talk about is how can we represent meshes or surfaces in a form of a network? And we will do this by representing the surfaces as maps. And we'll talk about certain really nice properties that emerge from that. The second thing that we will do is we will go from this representation then to a notion of a differentiable triangulation. That sounds like kind of unclear what that even means. What does it mean to have a differentiable triangulation? And in the second half of the talk, I hope I would be able to convince you that there is a formulation that allows this. In between, I will go into this notion of differentiable reconstruction, which is how do we enter this domain of surfaces from point clouds. So that's my agenda for the next 30 minutes or so. So let's go ahead. So the first part is, how do we go from a surface represented as a mesh to a network? And this is the notion of neural surface map that we introduced earlier at CVPR. This is work done with my student Luca and collaborators Noam and Boba. So let's do a quick recap of the data structures we have for surfaces. And for the participants of this workshop, we are all familiar with this, so I can go with this a bit quickly. So we have sign distance field, which is nice, but it has a constant memory footprint, but there's no explicit surfaces. Right? So if you follow deep SDF and the subsequent line of work, this is the representation they have underneath. If you have point clouds, very simple to work with, very good in that sense, but we do not have an explicit connectivity, and that often creates problems if we want to measure some surface properties. We can have a volumetric representation, but then it grows very quickly as in cubic with the number of voxel cells. So that's not the greatest, but it's also very powerful if we look at NERF and this type of optimization where the underlying representation is volumetric and some appearance properties is being optimized. Or we have our favorite meshes, but then the problem is it's not continuous under changes in triangulations. And this the problem with the underlying triangulation, you can see, is if we go and do any sort of mesh processing or mesh manipulation algorithm, as soon as triangulation changes, we have to worry about all sorts of problems like folding and the triangle aspects ratios being messed up, and all these result in very complex handling of triangles. So we need to have very special cases to handle them nicely. So that's what we want with. Hence, we are going to introduce this neural surface maps, which would have the nice behavior of it being continuous, and the memory is also going to be continuous, and we will have an explicit surface representation, as you can see. Okay. So the idea of neural surface maps to start with is very, very simple. So all we do is the following. So if we have the surface mesh given on the left, which is this cow model, we can map it down to a flat circle. And this problem is called parameterization. There are various algorithms which are known and are numerically very robust to get this type of a parameterization. For example, in our work, we use a slim parameterization proposed in 2017. And now the idea is we have a network, in this case, an MLP network. It can be a convolutional network, but in this case, an MLP that takes the parameterization and directly stores the map, and the map being going from 2D to 3D. So it's as simple as a black box or an MLP network that directly stores this parameterization. So it remembers exactly like from 2D to 3D, and I will soon talk about how we optimize for that. Right? So if you recall how deep SDF does, it's very similar. It's a network that remembers the SDF of a surface. Here, it's a network that remembers the parameterization of the surface. And now in the next few minutes, I will try to convince you that this is really gives us lots of advantages. So let's look at how well this works. So if we learn this parameterization, so these are a couple of examples where we have learned it on this model on the left, or the Rhino model in the middle, and the color means how much it deviates from the underlying surface. So look, so notice that the values are in the order of 10 to the minus 5. So even red means very, very low deviation, which means it's possible to overfit to these parameterizations very well. How do we overfit? We are trying to minimize this integration over going from the parameter, which is a given whether slim or your favorite parameterization, back to the surface. And it has two terms. One is the point-to-point distance, which is the first term. And second one, we also have the normal deviation. So we want to be very close to the surface. We also want to preserve the features. Hence, when we look at the models, you can see the sharp edges and corners have been nicely represented. Just for completeness, we are working with disk topology. So there is this blue boundary you see. So there is a discontinuity around the blue boundary. So the left or the right of the surface. Okay. So far we haven't achieved much other than overfitting to a given parameterization. But now we will see why this is a useful thing to do. So first is, we now have a network that maps that represents a phi function. Right? And this is a continuous measure at this point. Okay, so we have the phi function. So now we can measure directly distortion. How can we measure distortion? By taking the Jacobian of the phi function. So in this case, it's a mapping from 2 to 3 dimensions. N is 3, so it's a 3 by 2. And we can compute this matrix by taking the standard J transpose J. And why is this useful? Because this allows us at any point P to compute the isometric distortion. Similarly, we can also compute the conformal distortion. The exact formula is not important. But because phi is represented as a network, and we can directly compute the Jacobian by doing a backprop over the network that we have. So we can compute this at any point on the surface, right? Or any point on the disk that we have in 2D, and hence maps to the 3D surface. So at this point, what we can do is we can compute distortions at any point. Okay, now it gets a little bit more interesting. So now what we have is we have overfitted to a parameterization, which is the phi function, but that itself may not be very, very powerful. Why? Because at that stage, we had no control over the quality of the parameterization, and that's our next goal. So now what we are going to do is the following. So the phi function maps from 3D to 2D, or the inverse of phi, but the phi maps from 2D to 3D. But to improve the parameterization, what we do is we find a second function, which is h. That's what we optimize. And that's from 2D to 2D. So it takes the disk and sort of distorts the disk such that the total composition has a low distortion. Remember that we can measure distortions over phi directly. And just as a comment here, I want to say that because we could map the phi as a network, we can now compose networks and we can differentiate networks. And these are two properties we'll be continuously be using. So let's go into this a little bit more. When we do this, we are able to obtain a direct sort of parameterization, which is low in distortion, whether isometric sense or conformal sense. Now, here's the first sort of advantage that you'd see, that because we optimize over H, which is a 2D to 2D, we are never going to deviate from the surface. So it's always going to be the cow model, which is advantageous because we are trying to get a low distortion representation of the surface. So that's very, very good. And we'll see in a video a couple of slides later. So to recall, this is the distortion measure. This function, the phi function, is fixed. That's the overfitted network we have. And now we define the second function, which is H, which is a 2D to 2D function. So it takes a circle and maps it to something else, such that we care about the distortion of the composition of the phi and H. Note that phi is fixed, so we will only be optimizing over H. And now we can define the distortion of the total function only by optimizing over H. So this is geometrically the way to see is we are now moving the disk we had on the plane and distorting it such that the composition of the map has a low distortion, which is measured by the formula above. And because phi has been represented as a network, all these things can have a nice gradient and we can do it end to end. So here's some results. So we start with the overfitted network, which as you see is a unit disk. And then after we optimize, then the unit disk sort of distorts such that the composition, when we go back to 3D, has a low distortion. It's better to see in a video. So this is the starting map, which has a high isometric distortion. And then as we optimize this, you're seeing that the cells or the squares becomes zero, and this gets uniformly spread out. Okay? So this allows us as a first application to directly do fine parameterizations that have low distortion, either isometric or conformal. Now we can do even more, but we have to work a bit harder for this. We can now go from one model to another. And this is the problem of intersurface mapping, where we would like to go from this cow model to this cow model. Right? Now, let me set the context here. So what's going on? We are given two models, the left and the right model. And our goal is to find an distortion minimizing transformation that goes from the left to the right model. Okay. So far, so good. Now, how we start is we have two overfitted functions, phi and psi. That's given, that's going to be fixed. And the only thing we are going to optimize is this H function, which goes from 2D to 2D. Right? So this is going to be easy to map. And that's the only thing that we would have to optimize to. And this would allow us to take a point from here, go to the first domain, do a 2D to 2D mapping, and go back to the 3D again. And we can ensure that the total distortion is minimized over the whole surface. Maybe it's easier to see in this one. And if we follow this figure, I think it explains the whole motivation of why we do neural surface maps. So we are given two surfaces, S and T. So we have an overfitted function to S that takes me from a 2D disk to S, another overfitted function T that takes me from again 2D disk to T. And what we are trying to find is a mapping between T and S, which is a mapping F. Now, this, as we know from geometry processing, is a very hard thing to optimize for, and because if we have an underlying mesh representation, it's a nightmare to do the bookkeeping right, so that we have a true distortion minimizing transformation between the surfaces. Instead, what we are going to do is we are going to optimize not from F, but for H. Recall that H is a 2D to 2D mapping. How does that help? So it helps because now we can define or go from H to S via the composition as defined by the red arrow. And if we look at this composition, we have to do phi inverse and then psi H. The problem here is the phi inverse. Now, this phi inverse is difficult to compute and intractable in the network. So we need to have a different game plan how to solve it. And this we achieve by the common domain trick. So what is this method? So we look at a point in one of the domains, let's say a P. We know how we can push it forward through the first parameterization phi. We also know how we can push P through the other parameterization here. And now we know that if Q is mapped by a F, it better end up at the same point FQ. So we can write down this as whether we go through the blue arrow or the other blue arrow will end at the same point. So the P gets transported to the same points. And to compute the distortions, we can write down the corresponding Jacobian. And with a little bit of manipulation, we see that we need the JP phi, but we need the inverse of that. But now we don't need the inverse of the map. We only need the inverse of the Jacobian matrix. And we saw before that we can compute Jacobian matrices. So this constraint is easy to optimize for in the loss function. We need an additional condition to make sure H is indeed bijective so that we don't crumble up the two disks going from one to another. And this can be ensured by making sure that the Jacobian matrix is positive definite. We can have a loss for that. And we also want to map the boundary to boundary. The details, I will leave it to the paper. Okay, so now we are done. And to recall is what we are doing is phi and psi, these maps are defined once, so that's fixed. Once we have that, we are going to only optimize for the 2D to 2D mapping H, right? So that's going to be easy. And we do this by making sure that the map H is bijective, which is the constraints on the bottom left. And then we have to make sure that the Jacobian constraint that we have on the bottom right, that is minimized again by the loss. And when we solve or optimize for this, we get the network which gives us the map H. So how does it look? So we initialize this by a random map H, and as you see, when we go to this idea, to this David model, it just gets mapped to just a tiny part of the hair because it's just a random map to start, but it stays on the body of the hair or the head of David. So, and as the optimization proceeds, which is H is being optimized by gradient descent, this you see it slowly spreads and covers up the head of David. And finally, we get this optimized map. And now if you look at the cubes and the alphabets, you would see that it indeed goes to the right region and it keeps it isometric. So you can truly do surface to surface maps. But I didn't talk about here, we do need a few landmark points that the nose goes to nose and others. So these are all with 3 to 5 landmark points. Okay, so that's the whole idea of surface to surface maps using neural surface maps. Here's another example going from one cow model to another, and then we take the left texture and map it on the right. This is how it looks as we spin around. And I don't exactly remember this, but this is probably again with 3 or 5 landmark points. we can do more in the sense we can take these models and map it to not necessarily meshes, but analytical functions. So these are some classic analytical functions which define surfaces. Each of these surfaces, we don't need a neural surface map anymore because we have the analytical form. And then we can again find the neural surface maps or the intersurface maps. So we can map them to, did I miss it? So, yeah. There's something wrong with the animation here. So the color indicates how it maps. So we can map this, the head of this girl to these three surfaces, which are directly given by analytical surfaces. Okay? So that allows us to do intersurface maps, but you can easily sum it up for pairs of maps to get a mapping across collections. So in this case, it's a mapping between these three models, and it uses three landmark points, which are indicated by the red dots. And we can truly optimize for the sum of intersurface maps as shown by the three arrows. So in this case, we are optimizing for three 2D to 2D maps, H1 to H2, H2 to H3, and H3 to H1. And it works out really well in the sense the networks or the deep learning structures are really optimized for end-to-end optimization. To summarize this part, what we have is this notion of neural surface map that is differentiable, and we can compose them. And this is useful for various geometry processing tasks. We are looking at other tasks like registration, scan alignment, and other things. And we'll explore them as we go along. If you were excited to work on this representation, you can find the code on Luca's website. It has been available for some time right now. Okay. So with that, I would just jump ahead a bit. So in the remaining time, I want to spend on the second problem that I talked about, which is how can we truly differentiate on the surface? So in the first one, we represented the surfaces as maps, but now we are going to also optimize the triangulation over these maps. Okay? And this is an upcoming SIGGRAPH paper with Mary Julie, who's the first author here, with my co-authors Noam, Max, and Paul. So here's again with our grand goal that we want to have end-to-end optimization from point cloud to surfaces via differentiable triangulations. Okay. So we would go in this following pipeline. So we'll go from 2D vertices to 2D triangles, and that's the main part we will talk about. We'll talk about how to make it differentiable. And then from the 2D points to going to 3D, this is the neural surface map we already explained, which is the M inverse, depending on which direction you go. That's the part that is fixed for now. That means we have optimized for the neural surface maps. So I will not talk about that. I will mainly talk about how do we compute the gradient over triangulation. And once we can do this, we can link the two, and we'll be able to directly optimize for surface properties while optimizing for the underlying connectivity. So let's focus on that. And I'll talk about this in 2D because this is the main core of the problem. So assuming a bit of background in geometry, in computational geometry, if we are given a set of points in 2D, and let's say this is in the UV domain, it can be in the neural surface map domain, some 2D manifold, we are given a set of points, and the goal is to find nice triangles connecting the points. And we know this is possible by using Delaunay triangulation. And what Delaunay triangulation does is it takes Voronoi cells of the points, and based on the connectivity of the Voronoi cells, we can define this triangulation. That's good. but we get a lot more because these triangles are guaranteed to have nice properties. So they would have the maximum of the minimum angle. These triangles are well behaved, things are good. But what we really care about is now if the point starts moving, how do these triangles change? And that's the contribution of this work. And then we will look at the weighted Delaunay formulation, which would generalize this. But let me go back to the Delaunay case before going to the weighted Delaunay formulation. So what Delaunay triangle means, if you haven't seen it before, is the following. For each point, which is the gray point, we take the Voronoi cell. And then if we take 3 points, as denoted by the red points here, this triangle exists if the following is true, that if the circumcircle of these red points is contained in the intersection of the corresponding Voronoi cells. And I will explain this as we go. Okay, so in that case, we want this triangle to have a very high existence probability, a probability very close to 1. In the case when the points have moved such that the big red triangle no longer have the circumcircle property that we talked about, we want it to have a very low probability, 0. So instead of 0 and 1, we want like a probabilistic association of that, and somewhere in the middle, it will have a half probability. Right? Now, the whole contribution of this work is how do we define such a continuous scoring of triangles? Under the condition that the points, the red points or all the underlying points are moving. Right? So we want to get the score, the gradient being computed when the points are moving. Okay, so we do this by introducing what we call the reduced Voronoi cell, which is the following. So for this triangle, there are 3 corners. The reduced Voronoi cell means if I keep the solid red point and remove the other points, then the Voronoi cell, at the beginning, we had how many? Well, 3, we had 6 points, but after we removed the 2 points, we have 2, 3, 4, 5 points. Sorry, at the beginning, we had 7 points. We removed 2, we have 5 points. Reduced Voronoi cell refers to this blue cell, which is a cell which is the Voronoi diagrams of all the solid points, including the gray and red. Okay, so that's our reduced point. And now here's the main observation. If we look at the distance of the circumcenter to the boundary of the reduced Voronoi cell, that's going to be positive if the triangle exists. But in the other case that we saw, here the distance is going to be negative. Right? So we can use this distance as a soft measure of whether the triangle exists or not. And somewhere in between, the distance is 0, and that's when we will give this a half probability. Okay, so let's look at this again in a cleaner example. So we have 3 points, J, K, and L. That's the standard Delaunay triangulation. Here's the Voronoi cell for the jth vertex, and CI is the circumcenter. Here is another example when the points have moved. Again, now you see that the Voronoi cells are again in blue, and it's CI at the centroids. But now what we introduce is the reduced Voronoi cell, which is we take out vertices K and L, and compute the Voronoi cell, the blue Voronoi cell, which is J/I. That is the K and L vertices have been removed. And same we do it for this other example. And you can see in the left one, the D is positive. On the other side, on the second, on the right column, D is negative. So we can use this D to, via the sigmoid function, to define the S score, which is close to 1 if D is positive, using a sigmoid, which is a nonlinearity function, or S is small when D is negative in the here. And then if it's exactly the CI lies on the boundary, then this D value would be 0 and S value would be half. So all we have done now is under movement of the points, we have defined a soft probability for each triangle in this one, in this mesh, in this possible mesh. And that's all really we need. So now having that, now we can optimize over the triangulation by changing the weights of the weighted Delaunay triangulation. So we are changing the vertex coordinate and the weights. Note that both of these are continuous quantities that we can optimize for. But when we optimize, we implicitly are optimizing over triangle association, which we have made a soft version, and hence we can do the propagation of the gradient throughout, even with over the space of discrete triangulation, that we have a soft notion of triangulation. Okay, so how does that help? Because now we have this, each triangle has a soft probability S, so we can redefine any sort of phase function, whether in this case, how well the energy, how well the size of triangles are preserved, or how well the curvature is preserved, the standard formulas. All you need to see here as different are the weighting by this soft probability S. That's the main thing we are computing. Everything else are your favorite equations from geometry processing that you can use, and now you have to change by having a weighted probability. Okay, and this allows us to directly do gradient descent over the whole surface where we optimize for some properties. Okay, now that we have done the work, I can directly show you some results of how this actually works. So let me explain what you are going to see in the animation. On the left is a final required surface size. So we have given yellow means I want big triangles there. Dark blue means I want small triangles there. So the user have given this, and in the middle column, we will see the triangulation, and in the right side, we would see the energy of how well the middle column is matching the left column. So in the end, the color profile of the middle and the left should match. That's what we're looking for. Okay, so I will now play the video. So you see that it's optimizing for the weights, but as a result, we're optimizing over the space of all possible triangulations of the points. And you see that the color slowly goes and matches the left one. If you are if you're familiar with computational geometry, you would also know that because we have a weighted Delaunay triangulation with a sufficiently high weight, we can also ignore certain points. So if we are given the superset of points, the final triangulation may decide to leave out certain points, which is advantageous when we have outliers and other things. So here's some more results, and something I want to stress is there are specialized algorithms for doing this. What we show here is, here's a generic algorithm that allows end-to-end optimization by changing the notion of triangle membership, but it performs at par and sometimes better than specialized algorithms. Here's a more difficult example where we try to align to curvature directions. So again, the left one is a curvature field that's given as being the target. And in the middle, we have these triangles. And again, if we get to a pale yellow color, that means we have very low misalignment compared to the target. And you'd see these red compass like lines would eventually go and align to the underlying black edges. Again, I would play the video and please observe how the triangle edges are changing and aligning to the target red compass-like direction. I think this is really nice to see. Sometimes you'll see that the edge appears and goes back again. So kind of a flip, locally a flip, but globally here. But overall, you see that the color becomes paler and paler. That means the overall error is going down. So this is truly optimizing over the space of triangulation, which is the first, as we know. Again, there are specialized algorithms. So there's instant meshes that also allows curvature alignment. We are at par with their method, but again, as I said, the power of our method is generic and can be used for other target applications or objective functions. As we saw with neural surface maps, it's possible to work with analytical functions, as we see here. So you can directly give sizing fields on analytical surface and we can get a mesh, even though we don't have the underlying explicit polygonal mesh available. We just need a underlying surface to be available. So in summary, what we proposed were two main things. We proposed the neural surface map as a differentiable and composed and a block that can be composed with each other. And then we talked about the differentiable remeshing via this soft notion of triangle membership. In future work, we'd like to take these blocks and make them available and incorporate them as core blocks in neural network libraries, especially for 3D. And the codes for this parts I talked about are available online. And I hope that you would find it useful and you would use it for the exciting stuff that you're working on. So with that, I would stop the presentation here, and I'll be happy to take questions if there's any. If you have questions later on, if you're watching this recording later on, feel free to reach me directly over email. Looking forward to your comments and feedback. Thank you.
Thanks a lot for the presentation. Maybe people can also put questions in the chat.
We are also checking the YouTube stream, so you can also, probably there is a little delay in between, but you can also put the questions in the YouTube stream.
I think to summarize the talk, I think the main thing we are looking at is really fill in this one or two missing blocks we need to make this as a common block, like we have a rendering block right now that can be used in deep learning networks. And then it's not only us in geometry processing area, but those who are working in scan acquisition, appearance capture, and other things can use this as a module for their end-to-end optimization. Yeah, so the question is, does the current method need to have the same number of vertices as in the final? No, because we are, as I mentioned briefly, because we are using this weighted Delaunay formulation, with the algorithm can, by optimizing the weights, ignore certain points. That said, it cannot add a new point. So we need to have the superset of points or the superset of triangles available. So it cannot add points, but it can remove points. But we believe that removing points is important, as in outliers. So it solves an important aspect of the requirement that we had at the beginning. I don't get to see the questions on YouTube, so I'm just going to look at the chat here. So yeah, you asked a very good question about the genus of the surfaces. In the neural surface maps that I presented, it is restricted to disk topologies for now. So we can only go from one disk topology to another. Right? And these starting parameterization, it's just a way of initializing the optimization. There are existing algorithms to do this, but because we can optimize over this other parameter h that I showed here, so because we also re-optimize for the 2D to 2D parameters. So the first parameterization is not that important. What is important, or what is a limitation, is these are restricted to disk topologies, right? So we cannot go across genuses. So for the organizer, Geraldine and Ilke, I don't know how you want to handle it when we run out of questions.
Yeah, so I'm checking the YouTube stream. It is in sync right now. Like, they know that we are in Q&A and there doesn't seem to be any more questions. So I think we can continue with the program. Thank you, Niloy, for very nice presentation and very insightful future directions, actually. So, and I particularly like that your slides are super informative and super visual, and like we actually got to see like the core idea very nicely with the animations and stuff. So thanks again for being here, and hopefully we will see you in our discussion session if it's not very late for you, but yeah. Yeah, thanks again. So now I'm leaving the mic to Dana for the introduction of the oral presenters.
Okay, thank you. So we are just starting with the paper. The first paper is from Sabri Nathan and Dr. Priya Cancer with the title of Skeleton V3, Advanced Channel Attention Blocks for Skeleton Extraction.
Hi everyone, this is Sabri from Keynote. Today I am going to give a presentation about skeleton at version 2. This is the flow of my presentation. This time we participated in 2 competitions. First one is point skeleton competition. They asked us to extract the skeleton from the point cloud, and in the second competition, they asked us to extract the skeleton from the binary image. This is the proposed skeleton net version 2. In the new skeleton net version 2, we made changes in the network layers, and we introduced the attention layers between the encoder and decoder layers, and reduced the number of parameters compared with version 1. The highlighted yellow box represents the side layers, and we have used the unit architecture with the 5 encoder and 4 decoder blocks. Each decoder box is connected to side layers, which is further supervised by ground truth image. The highlighted box represents the dense channel attention layers. This is the proposed dense channel attention block. The dense connectivity and the convolution layers improve the information flow throughout the network, and the output of each layer is concatenated to the all subsequent layers along the channel axis in the network. The highlighted box represents the channel twist and the spatial excitation block. We use the CSSC as an additional attention which is applied on the output of each channel attention block in decoder. This recalibration encourages the network to learn more meaningful feature maps that are relevant both spatially and channel-wise. Next, address the channel we use to convolution block attention model inside by Samuel. This attention is a kind of general attention which is applied both to get the channel attention and spatial attention. Channel attention is created using global average pooling and global max pooling of the input features. and then applying a perceptron and then element-wise addition of these two features. For spatial attention, again two feature map has been created using max pooling and average pooling, and then a convolution operation is performed on the concatenated features. The final attention is the element-wise multiplication of these two attention features. In our experiment, we combine the binary class entropy and the Bayes laws together and use this loss function. Now let's talk about the pixel scatter training strategy. First of all, we randomly split the data into train and validation. While training, we apply data augmentation from minus 45 to plus 45 degree. And also we use the Adam optimizer for and set the initial learning rate by 10 to the power minus 3. The training process is evaluated using validation loss after each epoch, and the learning rate was reduced by factor 0.1.
Next, address the challenge we used convolution block attention model inspired by Shan. This attention is a kind of dual attention which is applied both to get the channel attention and spatial attention. Channel attention is created using global average pooling and global max pooling of the input features, and then applying a two perceptron and then element-wise addition of these two features. For spatial attention, again, two feature map has been created using max pooling and average pooling, and then convolution operation is performed on the concatenated features. The final attention is the element-wise multiplication of these two attention features. In our experiment, we combine the binary cross entropy and the Bayes laws together and use this loss function. Now let's talk about the pixel skeleton training strategy. First of all, we randomly split the data into train and validation. While training, we applied data augmentation from minus 45 to plus 45 degree. And also we used the Adam optimizer for and set the initial learning rate by 10 to the power minus 3. The training process is evaluated using validation loss after each epoch, and the learning rate was reduced by factor 0.1 if the validation loss did not decrease during 10 epochs. And the model stopped training if the validation loss did not decrease during 30 epochs. We use the same Adam optimizer and the same training procedure for skeleton image. Here we initially converted the point clouds into images, but we have not applied any data augmentation techniques. Here comes the results of pixel skeleton dataset. And the proposed model achieved the state-of-art results with very low computational complexity. And the skeletonate version 2, which trained on binary mask, achieved an F1 score of 0.7961 on the validation dataset. This is the results of the proposed model on the shape cloud point dataset. The results clearly shows that significant improvement in the state-of-art approach. These are the results of point skeleton and the pixel skeleton dataset test data results. We applied our pixel skeleton model on real-time images, and these are the sample output images. Thank you, everyone.
Okay, and sorry for the issue about the audio. Is there any question about Pepe? I think the authors also are here, so if the authors also would like to add some comments, they are welcome.
maybe a nice comment about the paper is that, like, thanks for actually trying it on different modalities in skeleton dataset, both for pixel dataset and skeleton dataset, and also the object dataset. So that's good to see that, like, all these approaches are getting more generalizable across these different representations. So that's just my 2 cents. Any questions from the participants from Zoom? I'm also checking the YouTube chat. Or the authors are here if they want to give a little bit more information about the paper, or like maybe like future directions and what it can enable in the next step of research. I see Priya and Sabari are here, so if you want to talk.
So I
Okay.
think if there is no question, we have like 20 minutes break, then we will come back with the spotlights.
I will just read what Priya just wrote to chat for the
Sorry.
YouTube. Yeah, she says that as of now they have not planned anything for future, and they don't have something to add. But thanks again for sharing your research. So, Anna, you have the mic.
Okay, sorry, I didn't. So yeah, we have like 20 minutes break, then we will come back with the spotlights. Yeah, thanks.
Thank you. See you in the spotlights.
So we can continue with the spotlights. So I see the next author also is in the call. So probably we can start the video.
Hello, everybody. I'm Encapsulates from CNRS and Sorbonne University. Today, I'm going to talk about learning Laplacians in GBHF graph convolutional networks. I will first introduce the problem, then I will show the main contribution, which is GBHF net-based Laplacian design, and afterward, I will present some experiments, and I will conclude the work. Graph convolutional networks, or GCNs, seeks to generalize deep learning to arbitrary irregular domains, like graph or trees or whatever. The success of existing GCNs, especially spectral ones, is highly reliant on the Laplacians, which capture the structure of the input graphs. However, graph Laplacians, especially when handcrafted, are powerless in order to optimally capture all the topological relationships between nodes in graphs, as their setting is agnostic to the targeted applications. For instance, node-to-node relationships in skeletons capture the intrinsic anthropometric characteristics of individuals, which are necessary for their identification, while other aspects are necessary in order to recognize their dynamics and actions. So in this contribution, we introduce a novel framework which learns convolutional filters on graphs together with their topological properties, and these properties are modeled through Laplacian operators, which capture multiple relationships on graphs through GBHF polynomials. So let's see how it works. Considering G as a graph endowed with a signal and a Laplacian matrix, the GBHF convolution of a signal with a graph filter is written as a sum over all the degrees of the GBHF polynomial of these terms, where psi is a signal, tk is the kth GBHF term, and theta k is the kth convolutional coefficient. In this equation, this product acts as a feature extractor, which collects the differential and the non-differential statistics of nodes as well as their neighbors before applying convolution. When considering the tensor of the GBHF terms and the loss function L, one can design the Laplacian L as a part of GCN training by minimizing the loss with respect to the convolutional parameters and the Laplacian operator. However, with this design, L is not guaranteed to be a valid Laplacian. So we turn instead the design of L into the learning of a connectivity matrix A while guaranteeing L to be a valid Laplacian. We consider different reparameterizations of L, including the combinatorial and the normalized, as shown also in the paper. For any reparameterization of L, the chain rule leads us to this new definition of the gradient of the loss with respect to the adjacency matrix as a product between the original gradient and a Jacobian matrix, which measure the derivative of the Laplacian terms with respect to the adjacency matrix terms. All these Laplacians are built upon either symmetric or non-symmetric matrices A, which are obtained using weight sharing on the GCN architecture. When learning multiple matrices or multiple GBHF terms, this allows us to capture different graph topologies and allows us also to enhance the discrimination power of the GCN representation without increasing the actual number of training parameters, as L is shared through all the GBHF terms. A sufficient condition that guarantees the non-redundancy of the learned GCN representation is the orthogonality of the GBHF bases here. And this is obtained by taking a new form of the Laplacian, which is normalized one, given by this expression where lambda max and lambda min correspond respectively to the largest and the smallest eigenvalues of the Laplacian, and I here is identity matrix. Let's see how it works in practice. So we evaluate our Laplacian design using two action recognition data sets, which are SBU and FPHA. In the first set of experiments, we show a comparison of our Laplacian design against two Laplacian baselines, which are handcrafted and totally learned ones. This is achieved for different degrees of the GBHF polynomial and for different setting of the Laplacian, including differential, non-differential, as well as combined. And as we observe here, we get the highest accuracy with our Laplacian design. We have the same behavior also on the FPHA data set. We did also some evaluation study, which shows the impact of the constraint, namely the symmetry and orthogonality with respect to different settings. And as we observe here, we get the highest accuracy when we combine both symmetry and orthogonality. This is some qualitative results, which shows the obtained adjacency matrices when achieving Laplacian learning, and these are the original ones. And as we see here, we are learning extrinsic characteristics into these adjacency matrices, which capture the best action recognition. And finally, we did some comparison of our Laplacian design and GCN network with respect to different related works in action recognition. And as we see here, we get the highest accuracy. And we have also the highest accuracy on the FPHA dataset. In conclusion, we introduced in this work a framework which allows us to design graph topology as a part of GBHFNet training. And this is obtained or captured by learning Laplacians whose design is constrained with parameterization, orthogonality, and symmetry. And these constraints act as structured regularizers that allows us to model the relationship between parameters in networks in order to enhance generalization. And finally, experiments conducted on different data sets show the outperformance of the proposed method against different baselines as well as the related work. Thank you.
Okay, thank you very much for Hisham Sahbi from Sorbonne University. If there is any question from the author, or if anyone, or if the author wants to add any comment or anything to add on the paper.
Do you hear me?
Yes.
Hello, everybody. I don't have anything to add. I would like just to mention that the extension of this work is ongoing, and it's about the application in general graphs, not only for skeletons.
Okay, thank you.
You're welcome.
So if there is no question, maybe we can move to the next paper from Sharjil Ali from Carleton University. I see he is also in the call. Maybe we can share the video.
We present our paper on the evaluation of latent space learning with procedurally generated datasets of shapes. Recently, many methods have been introduced for synthesizing 3D shapes using a latent space to organize the data into small dimensions, allowing for the synthesis of new shapes. Such models typically include both an encoder to encode the input shape and output it as a lower dimensional latent space, and a decoder which does the inverse by taking the latent space as input and outputting a reconstruction of the shape. These methods also allow for new shapes to be created through the interpolation between two latent vectors in the latent space. However, most previous work relies on a qualitative evaluation to measure the performance. We instead develop a framework for performing a quantitative evaluation, which uses known semantic attributes of the input shape to compare to. To do so, we create a method that takes these known attributes as input and procedurally generates a set of shapes to use for evaluation. Our procedural generation method is divided into two steps. Our first step uses a split grammar-based approach, in which our pipeline takes in a box as input and then recursively refines it into the desired shape through a set of boxes, which we call our box rules. Our next step can then refine these individual boxes into unique shapes and parts and apply deformations as part of our path rules, which is then outputted as a mesh. Both of our steps uses rules to construct the geometry. We define a rule as a function that takes in a piece of geometry as input and outputs a set of defined geometry. We can then group certain rules together to form a shape, which we call a grammar. We can define which rules to apply for a given shape using an input parameter vector in which each element and its values determine which rule to apply, either as scalar elements or binary elements. For our evaluation, we use a total of 8,800 shapes split into chairs, beds, shelves, and tables. Each dataset includes both the meshes, which are voxelized into 32 cube dimensions, and a set of parameter vectors. We evaluate our experiments on 4 deep learning models, which allow us to encode shapes into latent vectors. In the PJ, we base the neighbor calculation on the parameter vectors of the shapes. We base our evaluation methods on 2 criteria. The first is the quality of the latent space, in which high-quality spaces better organize the semantic attributes defined by their parameter vectors. The second is evaluating the interpolation quality. In this case, good interpolation capabilities imply that shapes are realistic and smoothly defined between the actual shapes. We can define the semantic similarity of shapes by using their corresponding parameter vectors, in which we compute a Euclidean distances between their parameters. We also apply this method for calculating the similarity between the latent space vectors. We can then evaluate the semantic organization by comparing these distances using the distance correlation. We also evaluate the directions of a latent space in order to assess whether it captures the variation of semantic attributes. For every dimension d in the latent space, we sort the parameter vectors based on the order of dimension d for all shapes. We then compute the total number of changes for each attribute in the parameter sets. Finally, we only count dimensions in which there exist attributes whose total changes are low outliers, which shows a correlation related to the latent dimension's direction. To assess the interpolation quality, we compare the similarity of interpolated shapes to their expected ones. We first construct a set which contains an expected shape and its two closest neighbors, determined by scalar attributes in the parameters. We then interpolate between the two neighbors in the latent space and compute the Euclidean distance between the interpolated and expected reconstructions. For example, we expect the midpoint interpolation of neighbors with width 0.2 and 0.6 to be similar to the shape with width 0.4. We present improved results from our paper in which our evaluation shows that in general, autoencoders exhibit the same correlation between the semantic parts and the latent space. We also note that latent space organization can also be demonstrated through our evaluation on the latent space directions, in which the PGAU contains the most meaningful dimensions. Finally, our results for measuring the interpolation quality indicate similar results, both for a quantitative and qualitative measure. In conclusion, we developed methods for the procedural generation of shapes using input parameter vectors that can then be used to evaluate the performance of various autoencoder networks for measuring both their latent space and interpolation capabilities. Our results have indicated that in general, autoencoders have the same degree of performance, with the DAU consistently performing the most. Thank you for your time.
Okay, thank you very much. So is there any question, or if the author wants to add any comment?
Hi, I can add a few comments about the paper. So as the first thing, something that we want to work on in the future was to increase the data set size, because we were quite limited because of memory constraints on the PC we tested with. So that's why it was only like 2,200 shapes per model. So in the future work, it would be, for example, increasing that to a very large number, like over 10,000 shapes was our original guess per iteration, and along with that, testing on more dimensions. So right now we only tested on 32 cube dimensions, but for example, we could do 64 even if we had less of a memory constraint. And something that was mentioned in the paper as well, I believe, was we didn't test on like newer based models such as GANs, for example, that's because they don't really encode the latent space. So that'd be something interesting to do if such a model were to come up with 3D shapes. We could work with that as well.
Okay, thank you. I see there is one question from Geraldine that she asked, how do you ensure independence to orientation?
Sorry, could you be more specific about that, please?
Yeah.
If Geraldine can, she can.
Mm-hmm. If you, so your model seems to be all oriented towards the frame. So what if you turn the model, if one of the chairs is, you turn one of the chairs 90 degrees, is it independent to orientation?
It shouldn't be. We haven't really tested on orientation much. It was just testing on exactly, as you mentioned, facing the front, more or less.
Mm-hmm. So I guess if you turn the chair, if there is no so like something that makes it independent to a rigid motion, then it should change the representation in latent space as well. Is that right?
It should, yeah.
Mm-hmm. Okay, thank you.
Okay, thank you very much. So we go to the next paper, which is from Shun Yao and Fei Yang from Computer Vision Center from Autonomous University of Barcelona. So maybe we can share the video.
Hello everyone. Today I will present our paper in the BLGC workshop of ICCV 2021 named 3D Shapes Local Geometry Codes Learning with SDF. So, let's start from a classic formulation for representing 3D shapes called sign distance function, which is used in a learning model named DeepSDF proposed recently to extract the zero-level ISO surface manifold of a 3D shape. However, the effectiveness of this model depends on the complexity of the 3D shape and the capacity of the neural network. For example, if we decrease the size of the SDF model, the accuracy will degenerate under the same training condition setting. Furthermore, if you look carefully into the details of the reconstruction result generated from the small model, you will find it is too smooth to hold the original local details. Our purpose is to alleviate this degeneration shown with the small size of DeepSDF network. We noticed that, in common situations, the complexity of an object part is more simple than the whole. So, why don't we use a set of local SDFs to represent a single 3D shape? With this idea, we propose to split space into different regions according to some key points as shown in figure. Then, we just need to model SDFs in these local regions and represent the whole 3D shape by the combination of those local SDFs. Since in a typical use case, the DeepSDF decoder can be made to represent a family of surfaces conditioning on latent codes. Thus, our another idea is for getting latent codes to model SDF in local regions. Different from the typical use of volume to put latent codes, we associate these with the position of key points, which is more flexible and could contain information about the spatial distribution of local SDFs. Inspired by geometric learning methods of modeling structure information, we propose to use a graph neural network to get a set of local latent codes from a global one. The graph neural network can help to propagate the information not only between the different layers' hierarchical structure, but also between the neighbor vertices in the same layers. This property is very important for training the local latent codes, since the uneven distribution of key points will cause an imbalanced number of sampling points for training the local SDF in different local regions. In other words, this uneven distribution will lead to some undertrained local latent codes since the less of supervised signals. The geometric learning could make these local latent codes not only learn from the sampling points, but also learn from each other. For an overview of our method, we use a mesh template as the graph structure to get local latent codes, where the vertices of the graph are also used for defining the local regions. So firstly, we use a graph neural network to transfer a global latent code into a set of local latent codes, which simultaneously provides constraints on the local latent codes with its neighbors to make sure each one gets proper training. These local latent codes will be sent with its aligned sampling points to a mini DeepSDF decoder. In this situation, we can just use a simple SDF model, which size has been greatly reduced compared to the original one. Let's have a look at our results compared to the others. From the visual perception, our results are even better than the original DeepSDF model. In quantitative evaluation, though the size of our SDF decoder has decreased dramatically, our results are better than the pure SDF decoder-based models with the same size of parameters, even better than the one with large size of parameters in the Euclidean distance metric. Meanwhile, our reconstructions have more fluctuations. We think this property not only provides the power of retaining details, but also suffers from the oscillation in too complicated regions. Here are some failure results of our methods. These are caused by different experiment setting, Please read the paper for more details. Thanks.
Okay, thank you. So I don't know if the author is in the call or not, but if anyone has any question, please write or ask. So then maybe we can move to the next paper from Shivanand Venkana from University of Delaware. I see that he's in the call, then maybe we can share the screen.
Hello everyone, I am Shivanand Venkana Sheshapanavar from the University of Delaware. Today I am glad to present Patch Augment, a local neighborhood augmentation in point cloud classification. Typically, points are augmented at the object level and then sampled and grouped to extract local features. However, object level data augmentation techniques are often applied to the entire object, ignoring the object's local geometry. Also, by visualizing, we understand that the group points are the same as the original input points. Furthermore, different local neighborhoods on the object surface hold a different amount of geometric complexity, and applying the same data augmentation techniques at the object level is less effective in augmenting local neighborhoods with complex structures. In this work, we apply patch augment to the group points called patches. Patch augment is a technique that can be plugged into models with layers containing neighborhood query. Our patch augment applies different amounts of augmentations to different neighborhood points. Hence, the number of points representing the object increases by several folds in the case of patch augmented grouped points. Consider an object after the sampling and grouping layer and a neighborhood at a specific point. Applying patch augment to these points is as follows. Patch augment randomly drops a small fraction of neighborhood points and randomly scales the group points. Patch augment does two types of rotations. Firstly, it rotates grouped points with smaller different angles along each of the axes, and then rotates along the up axis. The group points are then randomly translated. So far, the applied augmentation techniques are common to all points within a patch neighborhood, but different for points belonging to different neighboring patches. Finally, jittering is applied. Jittering makes the points move randomly within a neighborhood space. Jittering is different for each point within a neighborhood. We notice the changes in the points at the neighborhood level and hence at the object level due to patch augment. We also see an increase in the number of points in 3D space that represent the overall group points. Although these 6 types of augmentations are same as conventional data augmentations, they are not fixed in case of patch augment and are applied to each group neighborhood differently. Among the 2 popular types of neighborhood querying, that is the ball querying and k-nearest neighbor querying, we recommend k-nearest neighbor based querying for patch augment. The reason is that when ball query fails to fetch the requested points from a neighborhood around the centroid point, it repeats the centroid point. Application of patch augment to these repeated centroid points results in a lump-like parts as shown here. We evaluated the impact of patch augment on two of the standard models, PointNet++ and Dynamic Graph CNN, against 4 datasets and achieved decent improvements in 3D classification accuracy. We also show considerable improvements on all the 6 variants of the scan object NN dataset. On the hardest variant of scan object NN, both overall and average class accuracies of PointNet++ model improve by 3.1 and 4.3% respectively. We did a bunch of ablation studies to see how each augmentation at the patch level fared. We studied a combination of object level and patch augment on PointNet++ against ModelNet 40 and then Dynamic Graph CNN against ModelNet 40 and ModelNet 10. Finally, we also studied the change in performance of the patch augment with different augmentation parameter ranges. Thank you for listening. Please visit our poster session for more questions.
Okay, thank you very much. So if the author wants to add any comment or if there is any question.
I want to pose a question. So the results that you showed with patch augment is mostly for classification. So have you tried anything with segmentation or detection or pose estimation with these different approaches?
Yeah, I tried with segmentation and there isn't like much improvement. I could say like 0.2, 0.3 MIOU improvements with the segmentation. Yeah. So I tried those after I got the reviews where one of the reviewer asked me to check if it works for segmentation or object retrieval or anything of that sort. Yeah.
Got it. Okay. Yeah.
Okay, thank you. So maybe we can move to the next paper from
If Charlotte wants to add something, just like
yeah.
Do you want to say anything about the paper or add anything or about the future directions?
One future direction is right now the augmentations are like, the parameters are picked randomly. So one future direction is to learn these parameters and see how much amount we can augment a given neighborhood. Yeah.
Okay, thank you. So the next paper is from Soon-Young Song from E3. So maybe we can share the screen.
Good morning, everybody. Thank you for participating in my presentation. Today, I'm going to talk about my work entitled Unit-Based Autoencoder Architecture with Dual Input Streams for Skeleton Image Drawing. In this paper, we summarized our solutions for the pixel skeleton challenge. I'm the primary author of this work. The objective of this challenge is to make skeletonized images under the provided dataset. This challenge measures skeletonization results along F1 score that is the presented equation. TP, FP, and FN are true positive, false positive, and false negative for predicted skeleton pixels respectively. All samples for source and target element in the provided dataset are gray colored images with 256 by 256 pixels resolution. As shown in the figures, sources are mask images and targets are skeleton images. The total number of samples for train validation testing is 1,725. Additionally, we were able to symbolic labels for training and testing in the development phase. To solve the given problem, we focused on autoencoder models, such as UNet for semantic segmentation. UNet models can transform the information domain. In the upper figure, we know that the UNet converts an RGB images to a mask image. Likewise, we want to convert mask images to skeleton images. In our problem, the number of skeleton pixels is too rare than the background pixels. To compensate for the class imbalance, we propose the modified UNet architecture to feed the reference skeletons. We intended to use additional features from reference skeleton images during the decoding process. Each encoder extracts deeper and wider features with downsampling. Then the deepest features from dual paths meet at latent space. Finally, the decoder regenerates skeleton images by merging corresponding interlayer features and upsampling. To train our models, we use cross entropy and hybrid dice laws. The hybrid dice laws uses the dice coefficient and cross entropy. The dice coefficient measures the similarity between prediction and target pixels. This criterion leads predictions to make resembling targets. Data augmentation is necessary because the quantity of the provided dataset is insufficient to train our models for having adequate performance. We manipulated the trained masks and skeletons randomly by rotation, flipping, and resizing. We did not apply to some augmentation schemes such as erasing and masking to preserve geometric characteristics. Meanwhile, the proposed models require reference skeleton images. For convenience, we used legacy algorithms included in the OpenCV extension packages. To evaluate the system performance, we used high-end computing devices and Python-based deep learning and vision processing libraries. We considered the 5 deep learning models, 2 thinning schemes, 2 types of outputs, and 2 loss functions. Also, we used the learning rate scheduler to find the best model. As a result, our best model was the DISCO-B, which is a hybrid of UNet and U-transformer. We applied John's thinning method, cross entropy plus dice laws, and symbolic labels. Our best score was 0.6668 in 100 epochs. Our prediction score on the leaderboard was able to get by fine-tuning during 500 epochs. Our approach showed better skeletonization output than legacy algorithms in terms of branch recovery and denoising. But some results of the DISCO-B still showed to be disappeared skeleton pixels. In this work, we proposed the deep learning-based DISCO models dealing with dual images for skeletonization. With our proposed DISCO-B, we were able to record 0.7386 in the leaderboard of this challenge. Here we noticed some of the skeleton pixels for the DISCO-B still vanished. In the future, we are going to research to make reference skeletons with recent algorithms. We referred 13 technical papers. Thanks for watching.
Okay, thank you. So I'm not sure if the author is in the call, but if there is any question. No? Okay, so maybe we can move to the next paper from Xiajun Tong from Boy Technology Group. I see that the author also is here. So maybe we can share the video.
Hello, everyone. I'm Xiaojun Tang. I come from the BOE Technology Group in Beijing, China. In this presentation, I will introduce the distance and edge transform for skeleton extraction. In the pixel scalar light on challenge, shape images are provided and participants are asked to generate the corresponding skeletons. Both the shapes and the skeletons are represented as binary images. The challenge is posed as a pixel-wise binary classification task and evaluated using the F1 score. We formulated the skeletonization as a pixel classification problem and designed a pixel skeleton classification network based on the ULED architecture. Thanks to the downsampling and upsampling blocks, the ULED architecture has a large receptive field and is suitable for skeleton extractions. Instead of using the original shape images, we use the distance and edge transformation to generate SDE images and edge images and concat the SDE images and edge images as the ULED input. In order to improve the feature expressibility of the ULED model, a sequence of 3 rested blocks was applied in each downsampling block and upsampling block. In this paper, we used the SDE as the ULED model input, which might guide the model training to focus on the SDE range and help the model locating skeleton points more precisely. The SDE values are displayed in the bottom figure, which shows that the skeleton points are always located at the SDE ranges, while the hard distance estimation is sensitive to edge losses. The smooth distance estimation is much robust. Figure A shows the binary shape of a circle is rasterized. Figure B shows the estimated circle from the SDE is robust to edge losses. Whether a skeleton branch existed was dependent on the edge of the shape. The skeleton extraction model should pay more attention to edge regions. We propose to use an edge transformation and concat the edge images with the SDE images. In addition, a 1 pixel dilation and erosion operation was applied as a data preprocess. Finally, we use the multi-model ensembles to further improve the model accuracy. We show experimental results in this page. In the original ULED architecture, each downsampling block and upsampling block used the 2 convolution as basic process units, which could be replaced by other operations such as right-light blocks and dense-light blocks. The results are shown in the left table. A sequence of 3 right-light blocks achieves better F1 score. We compare the performances of different types of input data using the SDE and edge as the model input achieves the best F1 score. Finally, we got 0.81 F1 score on the Scalar Light On 2021 validation set. We simply extended the proposed method to the point Scalar Light On challenge and achieved 1.57 symmetric chamfer distance in the point Scalar Light On validation set. We also simply extended the proposed method to the parametric Scalar Light On challenge and achieved 6,407 squared distance score in the parametric Scalar Light On validation set. Thank you very much for your attention.
Okay, thank you, Xianju. So if you want to add any comment or your future work or anything that you didn't have time to add in the spotlight video, this is your time. Okay. And any question? Okay, so maybe we can move to the next session for the challenge overview.
Can everyone see? Everything is working? Sorry, I was like juggling between videos and questions and YouTube and so many screens. Sorry. So yeah, so as I mentioned in the introduction, we have two sets of challenges: skeleton in 2D and ABC dataset in datasets in 3D. So first, I will very briefly mention skeleton challenges. Then Sebastian will mention the ABC dataset and challenges. So okay, cool. So just a little bit of history of skeleton. There is a Women in Shape research network. Sorry, I'm reading the thing, organizing committee. Meanwhile, I should not do that. I'm really sorry. Okay, so there is Women in Shape research network, which is a part of AWM, and the history of skeleton goes all the way back there. So in 2013, there was lots of interest in skeletons and skeletons. I keep saying skeletons, sorry. In skeletons and how we do shape processing around like parameterized representations. And in 2016, which is the WISH in Trier, Germany, we wanted to compute better skeletons with learning approaches. So putting together like both the skeleton, the interest in skeleton extraction and the interest in like deep learning applications, we actually came up with that ScaleNet on challenges. So in 2019, we made the first skeleton challenge, and the WISH also continued this year in Oaxaca. It was supposed to be in Oaxaca, Mexico, but we actually did it virtually, unfortunately. But we had a very nice team. Again, there we are still working on it, and we are still using skeleton challenges. So that's a little bit of history. And some of the people that you see in the photo, Geraldine is there, I am there, I think Catherine is there, etc. So this is WISH. So geometric deep learning for shapes, we want to extend like the classical like recognition, detection, segmentation approaches to more global shape understanding and parameterized representations, and in future like hierarchical decomposition. So we organize this workshop to bring mathematicians, ML experts, deep learning experts, geometry researchers, and everyone to to create and co-create together based on the data sets, based on the baselines that we share, and creating global challenges so that like everyone can work on the same problem in the same setting with the same evaluation metrics with the same benchmark, right? And of course, then organizing a workshop to share all of those results from everyone around the world. For the skeleton tracks, we have 4 tracks, as I mentioned before. The first one is pixel skeleton, where we are trying to extract binary skeletons from binary shapes. So given a shape silhouette, can we actually find the actual skeleton pixels? So this may look as a trivial problem, but we want those skeletons to be robust. So if there is like boundary artifacts, if there is pixelation, if the silhouette border is not well sampled, then those are all the problems that may cause like overbranching, underbranching, as we see in the spotlight presentations, like vanishing pixels, etc. So how can we actually do this in the learning setting instead of the traditional like approaches where it may be a little bit less robust to those like artifacts? Then the second one is point skeleton. So we have the shape point cloud, and the question is, can we actually extract the point cloud skeleton point cloud from the actual shape point cloud? Now, this is like going a little bit more complex than the pixel domain, right? In the pixels, we only have the uniform pixels, like you can assume it is as a grid. So even the boundary artifacts or the actual pixel sampling, etc., everything is uniform. So in the point cloud domain, we don't know where the points are, if they are uniformly sampled, if there is like boundary artifacts are represented differently. We don't know whether some curvature on the boundary is actually a curvature for the real shape or an artifact because points are jittered, etc. So we want some deep learning. We want this to help develop some deep learning architectures that are flexible against noise, sampling density, etc. The third one is parametric skeleton. So this is similar to the first approach, but we are not looking for pixels on the skeleton. We are looking for a parametric representation for the skeleton. So the skeleton is actually represented by degree 5 Bezier curves in our like input-output relation, and we are trying to find that like continuous curves with the control points that represent the skeleton, which is a much closer way to represent the skeleton, right? Like if we are sampling the skeleton with points or with pixels, there will always be some discontinuity between them or some artifact if we zoom. But if we have like this continuous representation, parametric representation, then it will be independent of the scale, right? So this is we pose this as one step closer towards like global shape parameterization. Then we have our newest challenge, which is image skeleton. So going beyond image silhouettes, can we do that in natural images? And this is like here, all of them looks like living things, like the human, dog, deer, and elephant, but this is actually not skeleton in the sense of like biological skeleton, but skeleton in the sense of shape skeleton. So if you look at the data set, you will see all types of like I don't know, stars, like complex shapes, like everything that you can think of. So how the data set is collected, the skeleton extraction is done by interior bloom medial axis, so which are like equidistance from the boundary. But this suffers from robustness because small perturbations on the boundary, as I mentioned before, add additional branches, there are over branching, etc. So you can see like the classical, the classical skeletonalization versus the proposed skeletonalization. And we also play with the ground truth, like manually, like see if there's over branching, under branching, or some branches are not represented, or some branches are because of noise, etc. So we compute skeletons with different pixel thresholds, and then manually see which ones represent the shape better. So if you think this ground truth generation like humans are actually not really good at finding what is the exact middle of something, right? Like we can be good at like labeling things or annotating things, or like even maybe putting bounding boxes, not as much, but like some approximate things. But skeletons are exact distances, and we are not really good at that. So we still use an automatic system, approach to compute the skeletons, but we go over everything to find whether they are like really the shape or not. So that's the manual selection and manual removal part. So for skeleton pixel data sets, we have a combination of 4 different shape repositories. All images are represented by 256 and 256 resolution. We have shape silhouette images and skeleton images. We have 1,725 images with 90 categories. We divided the data set to 7% training, 15% testing, and 15% validation. And we have diverse geometries and topologies, as you see here, like all the way from that like weird spiral pyramid to the frog and the butterfly. Point skeleton, similarly, combination of 4 shape repos, similar point clouds. Everything is similar, but we also provide some sampling and noise generation scripts so that like you can actually augment that data, like do more sampling approaches. If you want to like try to generalize it to like more noisy point clouds, you can do that with the scripts, etc. The only thing that is different here is instead of labeling the points, we actually separate skeleton point clouds as different point clouds, or we can also do labels as point clouds. So this is maybe different. Third one is the parametric skeleton data set. So shapes as images. As I mentioned, skeletons are represented by degree 5 Bezier curves. We give the control points with parameters. Again, same number of shapes, categories, and splits. As the input, we give like CSV file with ordered control points. And for the branch ordering, we use WEDF. You can check the paper for the reference. It splits if it's continuous and merged if it's equal. And looking for the maximal WEDF measure along a branch to order them. The last one is image skeleton. Now we have many more images because those are natural images, easier to find. We have 53,000 images. Skeletons are represented as pixel labels. We have 17 categories now, similar split with different pixels, different resolution. And again, we have diverse categories, as you see here, diverse poses, diverse things, etc. For evaluation metrics, for pixel and image one, which are basically based on images, we use average F1 score. For point one, we use symmetric chamfer distance. And for the parametric one, we have 2 metrics combined in one metric. One is the branch ordering and one is the control point. So we want the most important, like the main branch to be ordered like high and the control points to be similarly to where they are given in the input. For the results and baselines, for the pixels, the vanilla Pixelpix gives 0.62% accuracy. For points, PointNet++ derivative with dynamic weights gives 0.58% mean IOU. For parametric, we have a modified ResNet 50 architecture to find the loss as we defined before. And for images, it's coming soon. So these are the baselines. By the way, these are the baselines that we published with the data set in the very beginning. So there are much better approaches that are published in 2019 and now in 2020 and 2021 versions of the workshop. So these are just the baselines that comes with the data set. as I was saying, check out the paper for more dataset characteristics. You can look at the previous editions of the workshop for finding the different papers. So they're always open. You can go there, download the datasets, submit your results, etc. Now I will give the stage to Sebastian for talking about ABC datasets and challenges.
Thank you, Ilke, for your presentation. So now it's my pleasure to present the ABC dataset challenge, which is the second challenge that we launched, or the second set of challenges that we launched next to the skeleton challenge. Unfortunately, we did not have many participants, so we didn't have, we had some participants, but we didn't have submissions that counted for the final challenge. So apparently it seems that the entry barrier for working with 3D data is still a little bit higher than for working with 2D data. Yeah, but nevertheless, we're gonna quickly go over the challenges. They are all available on CodaLab, and my colleague Alexei presented them in this video here. So we will play the video right now, and then if there are still questions afterwards, if the people have feedback why they couldn't participate, just let me know, and we can talk about it. Okay, so let's see. So this is the challenge video, and I hope that the sound is working as well. Can somebody let me know if you can hear sound?
I don't hear the sound.
Could you maybe try to share the video, Ilke?
Yes, I can. Just a second.
That would be great. So yeah, these are the people that set up the challenge here. So the challenge is based on the ABC data set, and we are running this for the second time. Last time we had a couple of participants. This time there weren't any submissions. So we're looking forward to actually get more activity on this challenge. Yeah.
We present ABC Geometry Reconstruction Challenge, a series of geometry processing benchmarks built on top of ABC.
Now, if I can find the Zoom window, I can share.
Just quickly had some sound, but okay.
This work is a joint. We present ABC Geometry Reconstruction Challenge, a series of geometry processing benchmarks built on top of ABC. This work is a joint effort between Dennis Zorin and Daniele Panozzo from New York University, Sebastian Koch from Technical University of Berlin, and Evgeny Burnaev, Albert Matveev, and Alexei Artemov from Skoltech. In this video, we describe the motivation behind our dataset and benchmarks, the structure and the available annotation in our data, and the challenges that are live now. We present ABC Geometry Reconstruction Challenge, a series of geometry processing benchmarks built on top of ABC, a big CAD model dataset for geometric deep learning. This work is a joint effort between Dennis Zorin and Danielle. Our website or search for ABC in CodaLab.
Sorry, what happened? Did it end, or? I think it just started, right?
Images, audio, and video to processing 3D and geometric data modalities such as graphs, surfaces, point sets, or meshes. This has led to remarkable progress in the geometric deep learning, aiming to develop specialized geometry-aware neural architectures. Being data-driven, these methods have benefited from the growth in available datasets containing 3D models. They include both 3D CAD models designed manually and provided as triangular meshes, and 3D reconstructions from scanned real-world scenes and objects, including humans. It is generally challenging to obtain regular geometric data such as uniform meshes. Thus, 3D CAD models directly modeled as meshes commonly suffer from being non-manifold and significantly irregular, while those reconstructed from real 3D scans provide noisy and incomplete geometry. One path forward may be to employ parametric CAD data collections directly, leveraging the exact sharp curves and surface parameterizations created by the artist. ABC is a dataset for geometric deep learning consisting of over 1 million high-quality geometric models, each defined by parametric surfaces and associated with accurate ground truth information on the decomposition into patches, sharp feature annotations, and analytic differential properties. Similar to vector graphics for images, this representation allows resampling the surface data at arbitrary resolutions with or without connectivity information. We gather the models through a publicly available interface hosted by Onshape, a modern cloud CAD system. Most of the 3D models obtained from Onshape are mechanical parts with sharp edges and well-defined surfaces. The original data is encoded in a vectorial CAD format. We sample and triangulate parameterizations of the patches, extract an explicit parameterization for each surface patch and curve segment, and release BRAP, triangle, meshes, and feature files. ABC supports a number of applications, including dividing objects into surface patches, estimating sharp feature lines associated with normal discontinuities, conversion of a surface triangular mesh into a boundary representation, estimating normals and curvature values from points or meshes, and shape reconstruction from point sets. To encourage research in these directions, we have designed a series of contests using ABC annotations, the ABC Geometry Reconstruction Challenges. Our normal estimation benchmark takes advantage of the analytic surface normals in the ABC, where they can be computed from the vector representation of 3D shapes. As input, we provide point cloud sampling of 3D shapes annotated with analytic normals. Each 3D shape is sampled with several resolutions of the input point cloud. Thus, we provide 3 datasets differing by point cloud density at 1K, 5K, and 10K resolution. We evaluate the result using a mean orientation similarity scores, treating normals as node-oriented. The results are averaged in each dataset with or without edges information. The normal estimation benchmark is live now. Go to adacid.group/3ddl/ABC Normals Challenge or search for ABC in Protolab. For 3D CAD models of man-made objects, ABC provides analytic differential quantities, such as normals. Some surfaces contain curves, where normals change rapidly in the direction perpendicular to the curve. We display these sharp curves in red on the right and design 2 feature line extraction benchmarks. From a discretized CAD model, we first crop multiple patches, and then compute point samples for each patch. Next, we use the point patch and the sharp feature annotation from ABC parametric CAD models to compute distances to closest feature lines and their truncated versions. For our sharpness fields extraction challenge, we provide the real valid distance values. For our geometric shape segmentation challenge, we threshold these distances. To provide a more challenging benchmark, we crop patches at 3 different scales, capturing increasingly larger mesh fragments, but sample them with the same number of points. Each dataset has 100,000 point patches for training the models. Both line extraction challenges are live now. Go to our website or search for ABC in CodaLab. We have introduced the ABC Geometry Reconstruction Challenge, a series of geometry processing benchmarks built on top of ABC. Thank you for watching.
Okay, thanks, Virtual Alexei, for that nice presentation. So everything else, all other details are available on CodaLab that you've seen on the link, like metrics and so on. So if you're interested, the challenges are still open and you can still participate. There's also code for loading all the data, so it should be fairly easy to get started. So I guess with this, we go back to Ilke to present the winners of the skeleton challenge. Is that right?
Yeah, we will not have winner presentations for Skeleton because we did not have enough participants to actually go to the second phase. Do you have winner presentations for ABC?
No, we don't have either.
Okay, then we can go to an early lunch break and then reconvene at 1 p.m. for Amju's keynote, if you want.
Awesome, looking forward to it.
Okay, thanks everyone. I hope everyone is like excited enough right now to go and download the ABC and Skeleton datasets and start working on it because this challenge needs winners, okay? Thank you.
Hi, Anju.
Oh my God. Yeah, how are you? So nice to see you.
Nice to see you too.
Oh my God, what are
Sorry.
you doing right now? And then how are you?
Good.
Mm. So nice to see you.
Likewise, yeah.
Oh my God. Oops. How are you? On YouTube.
Oh my
Okay.
God.
Right now, and then how are you?
Good.
Someone has a stream on the background.
Hello.
Hello, hello, welcome.
Hey,
It's
everyone.
always lovely to see you.
Yes, it's so nice to see everyone. Too bad we're not doing this in person.
Yeah.
Yeah. I see this is streamed to YouTube. I guess that's nice.
Cool.
Do we start on time or
Should we start?
Yeah, please.
Oh, okay. It's my pleasure to introduce Anju Kanazawa from UC Berkeley. Anju graduated from University of Maryland, and she mainly works on intersection of computer graphics, machine learning, focusing on visual perception. So without further ado, Anju, please go ahead and share your screen and we can start. Awesome.
okay, can you hear me?
Yeah.
All right. Thank you for inviting me. I would really appreciate if the organizers are here who could turn on their cameras because I don't really like staring into the darkness. Although I guess this is a stream to YouTube. Okay. All right. Thank you. Thank you. And my cat wants to go outside. So that's our background music. But all right, so today I'm super excited to talk about real-time rendering of NeRFs with planoctries, particularly because on the aspect of visual debugging, which I'm going to get into, but let's just get started. So I'm at this point, if you're in this workshop or interested in this topic, you probably have heard of this thing called neuroradiance field, which came out of Berkeley at last ICCV. And this approach is able to model these synthetic scenes really photorealistically, even real scenes. Okay, I'm going to. She just wants some attention, and here's some cats for the thing. Okay, all right. So NeRF in a minute. So here's a slide of a NeRF in a minute. So you may probably have heard of NeRF, but NeRF is an approach that it's a coordinate-based neural network, which takes in X, Y, Z in a view direction and outputs RGB sigma values. Okay. And then how do you train this thing is that you actually have all these cameras, all these scenes, you have all these pictures, and you're going to shoot a ray in the scene. You're going to ask your neural network at every single point on the scene, like what is the density, and you get this histogram. And then you integrate this ray values using this volumetric integration function, which is basically a function of the density and the color. And then you get a pixel, and you want to make sure that that pixel is similar to the ground truth pixel that is in the thing, okay? And then this has many different view directions, and you shoot this from different viewpoints, and you overfit this particular network to this scene representation. Because of this, this approach requires a lot of images that you have to optimize for every single scene independently to get this NeRF. But then once you do that, you can do all these cool view synthesis tasks. And because of this, there's been a lot of work and even more and more of these things that have been proposed. Okay, but of course, there's a lot of excitement comes, but with a lot of wish lists on what we could do with NeRF. And this is a slide from Matt Tansek, who is one of the my student and one of the authors of NeRF. And so there are a lot of things that we want to improve, right? For example, it's very expensive and slow to train and slow to render. There's all of this list. And we have been addressing a couple of these points in my lab. So for example, PixelNerf starts to look into the question of how can we generalize NERF to multiple scenes. And today I'm going to attack these aspects of the slowness of NERF. Okay, but before I get into how to make NERF faster, I think it's always important to talk about, why are we trying to do research in NERF, right? Like, I mean, it's cool and everything, but like, what's the point, For me, what I really am excited about is that volumetric rendering is a very effective differentiable renderer. So I've been working with meshes. Okay. Okay. So the properties of NERF that appeal to me is that it's a very effective differentiable renderer. Okay, so here is a visualization from the beginning of NERF. Okay, so to fit this particular chair. Okay, and we have this chair from different viewpoints, but this is like seen from one view. This is the color, this is the depth, and this is density or something like this. Okay, all right. So once I start this, you will see that it converges so quickly to the general rough shape of the chair, right? And then it's gonna take like 16 hours from here on. I mean, this is sped up and subsampled, but like this isn't like it's subsampled in linearly. It's like then it's gonna take like very, very long time to get all the tiny details. Okay, so let me play that again. So from the beginning, see how quickly it converges to the rough shape of the chair. And I really think this is a really nice aspect of this. And if you use any other like explicit representations like point clouds or meshes, although these things might change due to the discrete nature of these representations, the basin of attraction of this differentiable rendering is quite narrow, as opposed to NERF, thanks to this kind of like fuzzy integration that you do across the ray, gradient really spreads through the scene very quickly. And I really like that aspect of this because I think, at least my goal is to learn about the 3D world from images without 3D supervision. And in order to do that, an effective differentiable renderer is very important. So I really like this aspect. Okay, another reason why it's cool is because it's a compact way to model the planoptic function. And what is the v-planoptic function? And so this is a really great part about teaching, because now I'm teaching, I learn about all these really cool classic concepts. So the planoptic function was a paper written by Allison and Bergen in 1991, which answers the question of what is the set of all things that you can ever see in an image. Okay, and that is the planoptic function. So what does that mean? So let's take this is a conceptual experiment, okay? So let's take a color image and let's think about this one person in the middle, like staying at the specific scene with like a single eye, okay? And then let's parameterize everything that this person can see. And then you get something like this, which is the viewpoint. So this function, which is the planoptic function for the snapshot, models the intensity of light that comes into the eye from a single viewpoint, because eye doesn't move, and then a single viewpoint specified by the theta and the phi at a single time, and as a function of the wavelength to model the color or any other spectrum, which is quite intense. This is a fancy function. Okay, so if you can model this function, you can reproduce everything that this particular center of the point can see, and so this is one for the color snapshot. And if you generalize this to the entirety of the world, then you're going to get this 7-dimensional function, which is again the 2 direction of like where you're looking at, right? As well as the wavelength, but then also the time, and you're going to be doing it at different locations, right? So this is why you have that same picture of this globe, but like situated everywhere densely. And if you can model this can reconstruct every possible view at every moment, from every position, at every wavelength. And this is really the entirety of our visual reality, which is a super, super cool representation, or cool conceptual thinking about what you could model. So this is a super powerful, fancy function, which, clearly we don't really know how to do this. I guess for example, things like the street view, Google Street View, it comes close to this because you get to see, you know, samples of the 360 view at like discrete time steps. Okay, why am I talking about this? Because, you know, let's kind of like look at that function, but like, you know, squint on some of the stuff. So let's get rid of the wavelength because we will always be outputting stuff as RGB, and let's get rid of the time too. So then you get this function that is 5-dimensional, which is view direction and then the location. So does this look familiar? And it should be, because this is exactly what the NERF is modeling. And I think this pictorial view of this panoptic function over here is a really easy, intuitive way to understand what exactly it is modeling. It's basically modeling at every single point this kind of sphere viewpoints, right? So I'm going to come back to this insight later because it helps us make this faster. Also, you know, it's really trying to, it's using this coordinate-based neural network to represent this function. It's really trying to model this function, which is cool. It's really compact. Yes, it's markedly different from the past approaches, because if you start talking about a panoptic function, you cannot not talk about you know, light field and Lumi graphs, which are classic works that try to model the panoptic functions. But light fields and Lumi graphs are 2D slices of the panoptic function. Also, the surface light field is a 2D slice of the panoptic function, where the slice is a 2D surface, or like, you know, intrinsically 2D surface. And NERFs can actually model the actual panoptic function, including the occluded rays. I just think this kind of reorganization and revisiting of this old ideas is kind of interesting to understand the past work and the relationships and the potentials, and what is the difference from, like, you know, past work. Okay, all right. Anyway, so maybe we'll come back to that. So let's remember this, which we had this poster session this week. We presented this work at this ICCV. And so here is a demo where we are doing real-time rendering of these NERF scenes. As you can see, NERF can capture, we have this viewer where you can interact with it. Okay, and the most important thing is that you can convert your existing NERF to this format easily, so that you can actually do all of these visual debugging that is available to you. And you can insert these objects, you can slice things. Actually, we have a web demo, but this is a little bit early for me, and I have not been okay, but this is good. Okay, so can you see my screen? I guess you can't see my screen. All right, let's do some web demos. Well, let's see. Let's do a hot dog. So this is alive. Can you see my screen? My screen is very bad resolution, so I hope it's not too bad for you.
It's very good.
Oh, okay, good. But the thing is, my internet is really bad, actually, and so it is loading sometime. But you know, but this is actually the a little bit of a trade-off that we had. If you open it with a normal internet, this thing actually loads quite quickly. Okay, so here it is. Now we have this, and you know, I am sharing this Zoom and doing all of these things. So my GPU is, you know, working a lot. But here are some of this displays, and this allows us to kind of, you know, do a lot of things, like, you know, you want to slice your hot dog to see what it looks like inside the hot dog, if you're ever curious about this. And then you can do all of these visualization of the view directions by changing what the view directions would look like, and do all of these things. And so I think this is just immensely important, you know, when you are developing any methods, to be able to quickly do some visual debugging of this, you know, you can look at inside, you can see what it look like, you know. So this is really what I'm excited about. And the first author, Alex, actually made a tool so that you can easily convert your approaches to this, and hopefully you can play around with it. Okay, so that's the browser demo. And so let's get into the method. But before we talk about the method, let's understand why NERF is super slow. Okay, NERF is super slow because for every single pixel, you have to do many network calls. And so to render this 800 by 800 image, it takes about half a minute, even on a very high-end GPU, you know, because it's required to make like 122 million network calls. So why is this? And this is because ultimately for every single pixel that you're going to generate, you have to sample that, and then you have to shoot array. And on that array, you got to ask your neural network, what is the color and the density of these things constantly, right? And so this one, it becomes like a 100 million network calls, and this gets really slow. Okay, so you have to sample densely in R5, and this is very expensive. So whenever you want to make things fast, the approach is to cache. So why can't we cache this? Pre-compute where the density is, and only query if the density is above some threshold or something like this, which works well for the density. The reason why it is tricky to do this caching, to make it fast, is this view direction business, right? Like, storing the density in R3 is voxel. So that's possible. It's a sparse voxel. But once you get the viewpoint, it gets a lot to cache. And the viewpoint, you also need to discretize it. You don't know how much you want to, and the discretization is not very good. But let's recall this picture from a planoptic function again. Then intuitively, you would see that you can actually factorize the location of where the, spheres are and the view directions. And these are, you can factorize these things, as you can see from this picture. So what we do is to take on this intuition. So we're going to take the slow network and then the original NERF network, and we're going to do some magic to factorize the view-dependent components and the densities. Once you can do this factorization, you can store this in a pre-computed representation, like sparse voxels that are view-dependent, which is what we call planoctree, inspired by the planoptic function, since that's really what we're approximating. So that's the high-level overview. So let's dive into the details. So number one step is to factor out the view dependence effects, and then we can store it in an efficient data structure. How do we do this? So first, we have first part is to deal with this aspect, which is that you have to have this view direction, right? And so the key idea is to use a spherical function. Spherical function is a function defined on the sphere. You can query a viewpoint, query a point on the sphere, and it will give you some values on that sphere. Quintessential one, for example, is spherical harmonics, which is basically a Fourier basis on the spheres. And so spherical functions, spherical harmonic basis can be computed analytically on the fly by given any directions. It will give you the basis of however many bases you want to use. And then you can do a linear combination of these bases to get the color or get an intensity for every single channel. So this is what we do. Instead of having a network that outputs the color given direction, we output the coefficients of a neural coefficients of spherical harmonics. Okay, so spherical harmonic bases look like this. And then we are going to, so if we're using 9 spherical harmonics, we output 9 numbers for every single for one color channel. Right. Once you have these coefficients, you can add these basis functions together, which gives you this function that you can, spherical function that you can query with any viewpoint on the fly, and then analytically, and then get the color by just simply doing this linear combination. So basically what means is that if you actually store it as a spherical harmonics coefficients, at this time, you only need to cache this, and you don't need to go through to ask your network about this, because the basis are already given to you, and it's really just doing dot product. Our approach is not limited to spherical harmonics. You can use other spherical functions like spherical Gaussians, which we did try. We could have also tried anisotropic spherical Gaussians, but we didn't go that far because there wasn't that much difference between spherical harmonics and spherical Gaussians. And it's also possible to do a learn to basis function. You can learn this basis function instead of using fixed functions. I mean, spherical functions, spherical Gaussians also learn this function. But the one drawback of the learning a basis function, depending on how you do it, is that it's specific to that particular scene, as opposed to spherical harmonics is globally shared by everyone. So it's you have to cache less things. But this is the approach that is being done in FastNerf, and I think this way can have a little bit more expressivity in trying to capture specularity and such too. But then it also is another freedom, so there's a trade-off. Okay. So that's one method, which is train a new network that is NERF SH. Another way is that, you know, maybe you actually have a nerve network that you want to do visualization and you didn't want to train it in this way. That's okay, because once you have a normal network, you can always sample that network, sample that nerve, and then just compute what is the spherical harmonics coefficients that approximates your view direction network, view direction function, right? And so this is, you know, basically you just do least squares. You sample the points where the density is high, and you sample the viewpoints, and then you solve least squares for every single point, and that allows you to get this nerve SH representation. And if you want this to be really, really high quality, it's good to sample more, obviously, but for visual debugging purposes, you can do this in like a minute or so, and it will look fine. Okay. All right, so once we have this representation that has factored out the view-dependent effects, you can store this in an efficient data structure, which we call the plenoctree. Plenoctree is nothing but a sparse voxel, which stores spherical harmonic coefficients. So in every single voxel, the voxels only exist where the density is high, and inside each voxel, it stores these coefficients of the spherical harmonics. So here we have 9 of the first 9 for it. And then we have this for 3 channels, so total it will be 27 if we're using 9 bases. Okay. And so the conversion to plenoctree is quite simple. How you do this is you just take sample a nerve on a grid of resolution of 2n to get the density, and then you just threshold the densities that are small, and then you keep those, and you make this voxel, and then you just store the coefficients in the density found at these octree leaves. Once you make this structure, it's also easy to render this, which is you just shoot array. But now you don't have to, query too much, because if there isn't any density, then you don't have to. You can skip it because you've pre-computed this computation. So the number of samples that you're doing is much less, and this really gives you a lot of the boost in speed up. Okay, so this is the method, obviously, the thing is that there's always going to be trade-offs whenever you're making it fast. And often the trade-off is quality, visual quality, and then the speed, you know. However, the nice thing about plenoctree is that once you convert it into this plenoctree representation, you can still keep on doing fine-tuning on these values. So we actually don't really lose, we have a way not losing the PSNR actually is maintained. The trade-off that we mainly pay is in terms of storage, because depending on the thresholding, right? Like the more complex the scene, the heavier the sparse voxels has to store, and so the most, so that storage indicated by this like weight amount of the memory required is our trade-off. Okay, but either way, we can do this and get to 100 FPS or faster, which is 3,000 times faster than NERF. And here are some results where we show comparisons of different settings of different trade-offs. You can make them and then change it up to your application needs. Okay, so a small detail, because you are caching, you don't really want to cache too much, right? And so this NERF synthetic scenes are all taken from upper hemisphere. So it doesn't really have any supervision of what to do at the bottom. And it's a white background. So if you don't do anything and naively train NERF likes to not give you a flat, flat blank table, but it actually kind of gives you this fuzz that when you render it together, it actually looks like this white table. So like when you threshold it, it looks like this. And this is not very good, because then you're spending a lot of time, spending a lot of storage trying to store these like junk at the bottom. And so what we do is encourage train NERF with the sparsity loss, so that the density it can be minimized. And then after you train with the sparsity loss, it gets rid of this table basically. This is why when we just opened the hot dog, the inside of the hot dog was also sparse and empty. Okay. All right, and then the nice thing is that you can directly fine tune the octree values. And so here's a blow up. So once you convert your NERF SH to octree, maybe it looks like this, but once you fine tune it, it becomes a little bit more crisp. Okay, and which actually suggests you this possibility that, oh, maybe you actually don't need to train your nerve for such a long time, like 16 hours or 24 hours, but you can actually switch over to plenoctory. And so we did do this, where, you know, the training time is the total time that was required to train a particular model, and the PSNR is the quality. And so what we do is you train nerve SH for 3 hours and then switch over to plenoctory and then optimize just a little bit to get what the PSNR gets. So, you know, it still needs 3 hours in the beginning, and then you do a little bit. And so this is why this is the blue curve is the plenoctory curve, but you can see that it can get good quality in much less time than it would require for a nerve or nerve SH to train. Okay. Now, it would be nice if you could do this from the scratch, but then we still need to do the nerve SH in this, or nerve training in the beginning, to get the structure of the sparse voxels. And the structure of the sparse voxels is quite difficult to differentiate against. And so this is why we need to still train in the beginning to get the structure. But we're currently looking into if we can get rid of this altogether, which would be an interesting direction. Here are some results on real Tanks and Tempos dataset, and because we can actually fine tune, you can see that the fonts of some things are more crisp, and you can do this much faster. And here are other examples. Oh, oops, oops. Here are other examples compared with the original nerve visual quality comparisons. And we run it on most of the basic data sets and all these scenes from Tanks and Tempos. Oh, right. Okay. So I do want to mention that there are a lot of concurrent works that are trying to make nerve fast, and they're all different in slightly different ways. So I encourage everybody to check it out. And there's like a cool insights from each one of them. A lot of them do build on this fact of factorizing the VV points and then using a sparse structure to skip the dense sampling, because that's really where a lot of the improvement comes from. Okay. So please check them out. So now on to limitations in future work. So like as I discussed, the trade-off that we have is the file size. So the model size can be big, and as the scenes gets more, you know, complex, this can also grow. Online demo actually uses a lower resolution and a quantized version on top of this, so that we can load these files quickly, which is important for real-time applications. And because of this, the rendering speed can be still slow for large scenes because you still have to store a lot of things. You know, maybe a further sparsity loss, looking more into that could help, or converting the final representation to a surface light field-like representation can also help. Another interesting artifacts that we see is that the spherical harmonics are really peaky. The higher order spherical harmonics are really peaky. And so if you don't get view directions from like many view directions, when you set some coefficients, you know, it can look very, very vibrant, or, you know, when seen from unseen directions. So you can see, you know, the chair, you know, you never have training data of seeing this chair from underneath, but you can see that the green color is quite vibrant because this is a little high frequency. Using other types of bases can also help with this. And lastly, because it's a voxel at the end of the day, when you zoom in, you will see these voxel artifacts, and it depends. And you can do a better interpolation, but then obviously it would also make it much slower. No, it will make it, you'll have to pay for it. Okay, so in summary, we present an approach that factorizes geometry in view-dependent color inspired by the planoptic function. This allows sparse voxel caching with explicit spherical functions, which gives you 3000 speed up over the OG nerf. The neat thing is that you can directly optimize the plenoctory, so you can keep on improving your performance. And then because of this, because the spherical harmonics is a existing basis, you can convert your existing nerf to this, and it's really great for visual debugging because you can convert it very quickly. Alex made this super cool tool, which is Nerf Viz, which allows you to visualize your Nerf models and the cameras and a lot of other things, it's easy to kind of edit this, I think, because my students are doing this, to visualize your results for visual debugging. So, for example, here are some experiments that we were trying to do where we wanted to reconstruct a larger scene. If you're working with NERF, you know that there's a lot of crap that happens on the unobserved regions. So it's like super helpful to be able to like slice these things and quickly see it, because otherwise specifying the camera parameters to kind of how to look at it is like also time consuming. And this kind of thing is very important for fast development and understanding what's going on. So the first author, Alex, put a lot of time making all of these libraries available. So all of the code on Planoctree is available, and so is this NERF-Viz. NERF-Viz, we can keep on making it better. I'm excited to do it that way. So I'd like to thank this my team in order to finish this work, especially the first author, Alex, was undergraduate when he worked on this, and so double, great job to Alex. Okay, all right. Well, I'm happy to take any questions. Thank you.
Thanks, Anju. That was a great talk. Let me see if there are any questions from the audience. So there's a slight delay with the YouTube stream, so it takes some time to for questions there to get posted.
Maybe one question I was wondering is that, for example, for the scene with the house and the tree, the branches of the tree would depend on the minimum Planoctree that is there, right? So is there a threshold for like not trying to like go to the minimum possible unit, or how does it affect?
Yeah, that's a good question. So as the scene gets more and more complex, I guess it's a question of your resolution. So all of these results are mostly in like 512 cubed. And I think in some cases, we may have done 1024 cubes. And like, the higher the resolution you go, the more easier we would be able to represent these like sparse structures or thin structures. But then you also pay a lot more for storage. So really it's like that. That's the trade-off.
Okay, so maybe instead of, I don't know, like, would there be like more adaptive basis so that like, depending on the complexity of the scene, you actually use different priors per the grid cells?
Yeah, so yeah. So the basis function is more about the view dependence, and then the for example, trees and branches are a little bit more about like, where the densities are and how fat those densities are. But one approach you could think is that if you're getting to a more complex scene, and if you want to render that kind of scene fast, is to have like a dedicated, different, you can break up the scenes into pieces, and then have different storage. It's kind of like an engineering mechanism in that sense of how can you actually load lots of storage, because in practice you can't make this as a high resolution as you want and like really only focus the densities on those points, right? Because it's sparse voxels, that's okay. Depending on how you can store it. And the discrete representation of voxel can be handy because it allows you to cut things up and like move things around, a lot more easier than NERF. Although NERF also in practice, you can change the domain of the function, but it's a little bit more intuitive.
Okay, thank you. Yes.
Thanks for the question.
Sure. Is there any questions in the audience?
I have a question actually.
Okay.
So when you built up your octree, it's kind of recovering in some sense some 3D shape because you put the data where the 3D shape is. Mm-hmm. and it could be splats, but there you have spherical harmonics. So would there be a way to to slowly go or iteratively go to a 3D representation? I mean, you get more 3D than you have in NERF, right? Because you put back things in 3D space. So
Yeah, I mean, like you can always run like marching cubes in NeRF and then just stretch on the density and then also recover the 3D structure. It's similar to that in concept when you do it. So I don't think it's more 3D than NeRF. But I guess the regularization is that for us to do this cheaply, it would be nicer if this density was well distributed or sparse. I mean, and actually in NeRF there could be a lot of situations where you can see like a white cloud or like a blob or something like that really floating around. And so this is why the sparsity loss kind of helps get rid of those things and bring them closer to a more compact representation, which you might call a surface. And I know there are a couple of works that are trying to embed like a surface implicit bias into the neural net into NeRF so that they actually model surface. Like we don't go that far, but it could prune some of these aspects. But in a sense, it's not that different from what an essentially NeRF stores in terms of 3D, because NeRF does recover the densities.
So, just a follow-up question. So, would it be interesting to see if you can use this to render volumetric data, like not just surface?
Yeah, definitely. Yeah. This is very actually. I mean, in a sense, this is quite classic, and we're kind of going back, right? So I think research is quite like a helix, and you revisit the volumetric integration function has been around, and like the people before did explore a volumetric rendering with like these sparse voxel like representations. So we're really going back to it, and it's really kind of like adding this view dependence aspect on top of it, and how to do that in a smart way.
Again, sorry, going further. So in your experience, just these 9 functions is good enough. It doesn't improve that much if you go to like even higher harmonics.
Yeah, so we did some ablation study, and they basically kind of get similar numbers on this representation. The challenge is that like the more harmonics you use, the larger you're increasing your parameters, the more it is able to overfit, and the more storage that you're going to pay. So it kind of becomes that game. I was really surprised because spherical harmonics, usually we use an intrinsic images, right? And then they're known for not being able to capture these shiny things,
Right.
In this case, we're actually not doing the decomposition, we're directly baking in the colors, so it can actually capture some of these specular effects, but then I think the learned bases are actually better at that, for example. But then I was surprised to see that there wasn't that much difference with spherical Gaussians, because spherical Gaussians, I believe, is a way people address for this specularity issues, and it's a good representation. But basically it didn't make too much difference, so we just went with spherical harmonics in 9, which is kind of nice and simple.
Nice. Cool. Are there any other questions? Can't see anything from the YouTube live stream. All right, if there are no other questions, let's thank Angju again. Thanks for the great talk. Hopefully you will join us for our next.
Thanks a lot.
Thank you so much.
Yeah.
It was really great.
Thank you.
Yes. Thanks. All right, so we are 1 minute early, but that's good. So we'll now go to our talk. Let me find the schedule. All right, so we'll have our oral presentation, which is basically towards efficient point cloud graph neural networks through architectural simplifications. This is a paper by Shyam Taylor, Rene De Jong, Tiago Azevedo, Matthew Martina, and Partha Machi. I believe we have one of the authors here. So, Ilke, do you want to play the video?
Called Towards Efficient Point Cloud Graph Neural Network. Hello, I'm Shyam, and I'm presenting our work called Towards Efficient Point Cloud Graph Neural Networks through Architectural Simplification. I did this work over the summer while I was interning at ARM. I worked with Partha Maggi and other people in the ARM ML research lab. Graph neural networks are really one of the hot topics in machine learning right now. We've seen them applied to all kinds of problems in the literature. Drug discovery is one example, code analysis, chip design, fake news detection, recommendation systems. These are all potential application areas that we've seen in the literature. We're going to focus on point clouds for this talk. If you look at any recent point cloud paper, the vast majority of them are using graph neural network-based solutions to process the data. They provide a nice native way of processing the data without necessarily having to translate the data over to some other modality. So one method before the advent of graph neural networks were approaches like multi-view CNNs, where we projected the points to an image and then applied a CNN. Whereas using a graph neural network-based solution allows us to basically process the points natively. In recent years, we've seen 3D scanning technologies become more common. We've already started to see them integrated into smartphones. So for example, the latest iPhones include LiDAR sensors. We can also expect them to see them integrated into mixed reality headsets when they finally arrive on the market. The question is, can we actually design techniques to process these point clouds that run on device without having to send the data off to the cloud? On-device inference would enable us to offer a better user experience, since it often provides lower latency without any constraints related to networking. Current models are too inefficient to run on these resource-constrained devices, and really this is what our problem is trying to solve, our work is trying to solve. Before I move on to discussing our work, I'm first going to talk about how GNNs compare to the more familiar CNN models. Just like CNNs, GNNs also share weights across the input. However, a major difference is that we can no longer make any assumptions about the size of a node's neighborhood or how that neighborhood is ordered. Secondly, we must use this highly flexible message passing paradigm, which allows us to describe how nodes send individual messages to each other. This provides us a huge amount of flexibility, but can be a burden from an efficiency perspective, as we will see in a minute. Finally, with GNNs, we must define a way to aggregate the messages that nodes receive, and this must be permutation invariant. Overall, the lack of regularity makes optimization very tricky, and most of the work in the field focuses on improving the accuracy without really giving much thought to how we can improve the efficiency of our models. Let's zoom in on the source of inefficiency that we're going to address in this work. On the left, we can see a graph model where the message function is defined to be a function of both the source and target representations. This means that we must explicitly calculate each message since it corresponds to an edge in the graph. On the right, we have messages that are just a function of the source node, which means that actually we only need to calculate the message for each node once, and then we can reuse it and just propagate it around the graph using something like an adjacency matrix multiply. If the number of edges is much greater than the number of vertices, which it usually is for point cloud models by a factor of 20 times, then we can dramatically reduce the number of operations that we must perform by forcing our model to fit the constraint on the right. This is the focus of this work. In this work, we're going to focus on two architectures, PointNet++ and DGCNN. Both of these works have received well over 1,000 citations and are among the most common baselines. As you can see, the models use message functions that are functions of both the source and target nodes, since they use these subtraction operations to centralize representations relative to the target node. As we've already discussed, this is really what we want to remove. So this is what the rest of this talk is going to focus on. The obvious first thing to do was to simply try removing these centralization operations by simplifying the message function to simply be an MLP applied to the source representation. This immediately reduced our message calculation costs by around 20 times. However, we saw a very noticeable reduction to model performance when we tried this. On ModelNet 40, we saw accuracy drop by as much as 3%, which is huge. And for S3DIS, we saw MIOU drop by 4. These drops are not really tolerable, we think, for most applications. So we then came to the next question, which was, well, how much of a model can we simplify? Can we simplify most of the model? Is there any layer which is particularly important? And how much of a performance gain can we get by applying this approach? We spent a bit of time scratching our heads, and we arrived at a hypothesis that the model performance was being dramatically affected by the first layer. Succinctly, we believe that there's an information bottleneck at the first feature extracting layer, where we often just have raw point positions and nothing else. If we fail to extract useful features from these raw positions, then the model performance will suffer. By contrast, after the first layer, we don't really need these sophisticated message functions. After all, they are not especially common in other application domains that GNNs are applied to. And actually, they could just be inducing overfitting as well. So we should be able to just remove them as long as we keep the feature extraction there. To be clear, our hypothesis has two useful implications if it is true. Firstly, if we want to improve the model accuracy, then what we should be doing is devoting more resources to the first layer, where we're doing the feature extraction. And secondly, if we wish to accelerate our model without necessarily impacting accuracy too much, then we should simplify everything except this first feature extracting layer. We tried out our theory on both DGCNN and PointNet++. Here's one experiment from the paper, but there are many more you can take a look at. If we use a baseline DGCNN model on S3DIS, we get an MIOU of 53.1. Obviously, the baseline experiment of just simplifying the entire model, it doesn't work. The model performance drops by 4 to 49, and this is really an unacceptable drop. Next, we tried simplifying just the feature extraction layer and nothing else. But as you would expect, based on our hypothesis, the model performance dropped pretty substantially in that case as well. Finally, we tried to simplify the model except for the feature extractor. That is to say that actually we kept the feature extractor unmodified and simplified everything apart from that. And what we see in this case is actually the model performance improves, supporting our hypothesis. We took our hypothesis to its logical conclusion and considered adding a few more geometric features to the feature extractor for DGCNN, such as the distance between points. When we use a more powerful feature extractor, even with a simplified backbone model, we achieve better performance on both ModelNet 40 and S3DIS than the baseline model. This means that we've actually managed to reduce resource consumption and improve accuracy at the same time. We find that we achieve up to 4.2 times speedups on CPU and 2.5 times on GPU. We also achieve peak memory reductions of up to 72.4% relative to the baseline, a substantial improvement. Some listeners may be wondering why we would go through all this bother. After all, can't we just use CNNs, which have seen huge levels of optimizations in recent years and have dedicated hardware support? Multi-view CNNs remain a solid baseline in many cases, as shown by our recent work at ICML. We argue that in practice, they are not really a good alternative. In the literature, it is known that these models are not especially robust, and we reproduce this phenomenon in our own work. We compared our model to SimpleView, a recently proposed multi-view CNN baseline, and we see that our approach can tolerate far more points being dropped than SimpleView. In practice, model robustness is an extremely important aspect for real-world applications. Finally, we're also curious whether our observations explain why there has been a proliferation of transformer models designed exclusively to handle point clouds. For example, there is a work at ICCV this week called Point Transformer. Why do we need these specialized transformers? After all, for other data modalities, they've coped with relatively few modifications. We think the reason for this is, once again, related to the input representation. We tried feeding raw points into a transformer and got really poor results, as you would expect, really. However, using a specialized positional encoding for each point does improve the performance a bit. But we find actually using a full feature extractor, which we have already built during the course of this work, puts the performance of an otherwise unmodified transformer model on par with the state of the art. We think our hypothesis underpinning this work has, is important beyond just the scope of this work, which is attempting to make models more efficient. I will end by discussing future work that is worth investigating. Firstly, we know that making our models deeper can be very useful for extracting better performance. This was shown by the work on POSPOL. But the issue is that these message propagation steps are really very slow, and they are now the bottleneck. It is really an open question how you can actually speed up these operations. But if you can, then you can improve model performance very substantially. Secondly, we did some profiling of these models on real-world accelerators that you might find in a smartphone or smaller device. We found that these models are actually extremely memory bound and achieve very poor accelerator utilization. To alleviate this will likely require us to rethink the model backbone design. This lies beyond the scope of this work, but it would be interesting to look into for sure. In summary, we have discovered that the feature extraction layer matters a lot for models operating on point cloud data. Improving the feature extract can improve model accuracy, and simplifying the rest of the backbone can allow us to accelerate our models. Our simplified models can yield up to 4.2 times speedups and 72.4% reductions to peak memory consumption. That is all I have to say. Thank you for listening, and please feel free to reach out if you have any questions.
Awesome. Thanks for the great talk. Let me see if there are any other questions from the audience. In the meantime, you mentioned that going deeper helps. Are there any rule of thumbs on how much deeper is good enough?
I don't think anybody knows for sure. I think this is one of those things where I think the models that have been built before basically reach the limits of what you can fit into your GPU, and then that's kind of it.
Got it.
I think there is evidence. There is papers, I think the POSPOL paper kind of discusses this. But yeah, I think it's one of those things where people don't really know, and the reason people don't know is because they're so inefficient. But it's not really possible to test.
Got it. Cool. Thanks.
I have maybe a tentative question. I'm not sure that's really relevant, but you would tell me there is this KP-conv paper where it, this paper on 3 points clouds where it makes convolution. And by removing the dependency on the like you are doing, are you not doing something that is going to converge to this KP convolution?
No. So KP-conv is. So I did also look at KP-conv, although the details aren't in the paper. No. So basically, the situation with that is, well, I think there was that slide where I had one thing on the left and one thing on the right, like the red green. Yeah, they're definitely very much on the left side. So making that more efficient is not easy. I don't think there's a very obvious answer to that one, basically, as to how you can make that one more efficient without losing some kind of, without using some kind of geometric significance.
Okay. Yeah, thank you.
Thanks. I don't see any other questions. So if not, let's thank the speaker again, and thanks again for the great talk, and hopefully you'll stick around for the final discussions session. All right, we have 3 more minutes, so let's just wait 3 minutes before Justin can start giving his talk, and maybe you can test your screen sharing now.
Sure. Yeah, happy to do that. Let's see. Okay.
Yeah, that sounds good.
All right. So we're just hanging out for now.
Yeah. Just so that we stick to time. So.
Okay.
Awesome. How's everyone doing? Like enjoying your day full of geometry and deep learning? It has been like a full agenda for us. I don't know whether you were with us for like some people were like with us through the whole day. So thanks for sticking with it. Like I know that it's too much information to absorb in a day, but hopefully we have all the papers out there, we have all the demos out there, we have all the challenges and data sets out there. So hopefully there is enough material to like not leave it in this day, but like use it, like make it useful for the rest of your research agenda. So anyone want to share anything in this next 2 minutes about the workshop and how it is going? I will take the silence as a good indicator that no one is complaining.
Yeah, as you say, it's quite dense. It's so we need some time to.
That's right. I know. And it started at 6 a.m. for me, so I'm like now I'm getting more awake for the talks.
Yeah. It's always with COVID. I've had talks where I had to give it like 6 a.m. or 3 a.m. and it's good in one sense because you don't have to travel, but still it's weird in other ways.
We are all looking forward to old school conferences.
Right.
I prefer to be jet lagged in a place that I go. I don't want to be jet lagged in my own house.
Yeah. Yeah. I gave my first in-class lecture last week, and it was after a year and a half, and it was interesting. So
yeah,
you
can start with the intro. Yeah. Okay.
Yeah, we are right on time. So today we are very happy to welcome Justin Solomon. Justin is a associate professor of electrical and computer science at MIT, and he directs the geometric data processing group. And he works on several problems at the intersection of geometry, optimization, graphics, vision, and learning. Without further ado, Justin, I will be going to talk about geometry processing inspired deep learning.
Thank you so much for the introduction. It's really a pleasure to come chat with everybody. Just to double check, you can see my screen, hear me, all that good stuff? Excellent.
Yeah.
All right. Well, this is my first time at ICCV, as it were. So I'm enjoying the experience, despite what I'm told are uncommon circumstances here. Right. So I'm here to tell you all about some of the research that some of my students and I have been doing in the intersection of geometry processing and deep learning, which I thought was kind of aligned to the topic of the workshop here. For those of you who I haven't had the pleasure of meeting yet, I'm talking to you from my office here at MIT in Boston. It's a ridiculously sunny and beautiful day outside, which we're lucky to have. We're on kind of borrowed time at the moment. But essentially, I run a group here at MIT that studies a lot of problems at the intersection of learning and geometry. So if you ever find yourself in Boston, of course, it's always our pleasure to chat and share all the different fun topics that we're up to. Essentially, our research sort of focuses on two clusters of problems. One, which we'll focus on today, involves applying machine learning to geometric data. So problems in vision and graphics involving 3D shapes and so on. The other half of our research group studies more abstract geometric problems in high-dimensional data analysis using tools like optimal transport, which is a lot of fun, but a little bit less relevant to our discussion at the moment. So we'll defer that for later, although if there's extra time, I'm always happy to tell you all about those kinds of things as well. So in today's talk, I thought I would focus on a problem that we've really thought about for, gosh, a number of years now, which is scary to think about, which has to do with machine learning from geometric data, and specifically deep learning from geometric data. Of course, I think that's probably the topic of most people's research in the entire workshop today. So it's always fun to find an audience of sympathetic colleagues here. But today I'm going to focus on some of the sort of basic operations in terms of what does it mean to make a machine learning tool that ingests a shape and then tells you something about it, and how does developing an architecture for this task really differ at a fundamental level from how we tend to design machine learning style architectures for images, volumes, and other kind of more standard structures. Now, of course, many of us in this call, probably many of you are more familiar with the challenges in this space than I am, know that there are so many difficulties when it comes to working with shapes inside of a machine learning pipeline. Of course, you know, in many of the research papers that we see at conferences like ICCV, all of the machine learning tools are built on one standard operation, which is convolution. And of course, we know that 3D geometry doesn't admit any standard notion of convolution, although of course there have been many attempts to come up with some notion of a convolutional neural network on a 3D shape, including some from our group. In fact, just in the previous talk, I was really excited to see our colleagues that are working on accelerating our DG-CNN architecture. But of course, there are many other challenges as well when we work with shapes. You know, shapes tend to be irregularly sampled. The types of noise that we see on a shape is quite different from what we might observe on images or other modalities. And this last point, which is one that I'm really going to focus on quite a bit later, is that working with shapes doesn't tend to be a GPU-friendly operation. In particular, triangle meshes, which are the sort of standard representation of 3D geometry in computer graphics, are irregular, basically graph structures, and come with all the same challenges that many of our colleagues in graph neural networks are trying to tackle for that kind of more general case. But at the same time, if we want to work on bringing machine learning to 3D modeling, computer-aided design, LiDAR, autonomous driving, virtual reality, we need to tackle these sorts of fundamental questions. And from my perspective, I think that there's some really interesting challenges in sort of asking these questions of, you know, if we weren't embedded in this larger computer vision community that has these extremely popular approaches to processing images, and we were just asked to build from the ground up a machine learning pipeline that makes sense for shape, you know, what would that look like, and would it really look like the architectures that we have today? So anyway, all of this is just a long-winded way of sort of communicating what I have on the slide here, which is that I would argue many of the architectures that we all know and love are really optimized for images like the left-hand side, which come on nice grids and are relatively controlled. But if we want to focus on structures like meshes, there's still quite a bit to do. So today, I thought I would try and bring a couple of our research papers together under one theme, which is that we can take inspiration from sort of classical approaches to geometry processing and processing of 3D data to inform how we might design architectures for learning from 3D shape. Now, interestingly, one of the kind of funny things about geometry research that I've noticed over the years is that geometry tends to be like a sub-discipline of a lot of other fields. There's like geometry for computer vision and geometry for medical imaging. And only relatively recently have the geometry people kind of stood up and tried to make their own community. But in the geometry processing for computer graphics area, there's sort of a very standard set of practices and techniques out there that we use to engineer techniques for understanding and processing 3D shapes. So the typical aesthetic that shows up a lot in this discipline of geometry processing has to do with building operations and algorithms out of, or rather building operations for processing a 3D shape that are really built from constructions that make sense for an underlying piece of smooth geometry, right? So we talk a lot about designing our algorithms to work on some smooth manifold and then discretizing using techniques like finite elements. Rather than just kind of navigating meshes and point clouds and so on as discrete objects from the ground up, right? And so, for example, oftentimes a phrase that you hear in this community is convergence in the limit of refinement, which refers to the fact that we want our algorithms to become sort of predictable as we have finer and finer approximations of a shape, right? As we sample them more and more densely, we expect the behavior of our techniques to kind of approximate some smooth integral over a continuous domain. And so in geometry processing, we tend to construct our algorithms out of like integrals and derivatives along manifolds using techniques like partial differential equations or PDE and spectral problems to understand geometry, because these are the things that are sort of standard in the differential geometry community and have a long mathematical history. In fact, one of the focuses that comes up a lot in this area is this idea of structure preservation, which is to come up with geometric algorithms that actually have properties that sort of resemble the ones that we know and love from smooth shapes. So for example, we know that the integral of Gaussian curvature over a surface is some topological invariant, so a very typical thing when you discretize Gaussian curvature on a triangle mesh might be to come up with one where when you integrate it in a discrete way over your mesh, you get that same invariant rather than just some approximation. So anyway, this is sort of a large body of techniques that has been developed over the years in the graphics community, sort of orthogonally to machine learning. And I think a really fun question would be, rather than starting with popular architectures in computer vision and making them work for shapes, can we make geometric deep learning techniques look more like geometry processing? So today in our talk, I'll try to share a few attempts that our group has had to build from the ground up these architectures that ingest a shape and try to learn signal either on that shape or about that shape, where at every single turn when we're doing our engineering, the decision we make is to try and make our architecture look like something that a geometry processing researcher from 15, 20 years ago would be comfortable with. Right. So in other words, rather than sort of forsaking the standard practice and shape analysis to make architectures that are more amenable for like GPU-based backpropagation, instead, we're going to try and use just standard geometry processing operations and then cope with the engineering challenges that come up when we start to introduce the typical differentiable machine learning style techniques that are popular today. So in particular, I'll tell you about our efforts to do machine learning from two different shape representations. One is a triangle mesh. This is sort of the typical shape representation in simulation, computer graphics. And then some other work involving geometry processing on parametric shapes. So think like CAD models and things constructed out of spline curves or subdivision surfaces and so on. And in both cases, what we're after are techniques that either input or output 3D shapes. And every single layer of our network, our processing technique is really built on operations that are sensible from a shape analysis perspective. Of course, you know, as a PI of a group here at MIT, I don't have the luxury and the pleasure of doing all the interesting stuff. Really, it's my students that are doing all the fun and work and are the insightful people in our group. And of course, really, I should credit my student Dima with doing the heavy lifting here. So of course, you should direct all of your interesting and difficult questions to him. Dima is also on the job market right now, so I would encourage you to talk to Dima if you have some interesting openings. In any event, let's get started. And first, I'll tell you about some techniques that we've developed for machine learning from triangle mesh structures here. In particular, a architecture which we just presented at the SIGGRAPH conference last summer, which we called HodgeNet, based on this sort of Hodge decomposition and assorted structures, the Hodge-Lopatian, that show up a lot in the geometry processing domain. So the starting point for understanding this algorithm and this architecture comes from this sort of basic constructions in geometry that I think are quite familiar to many people in our audience here. Now, essentially, over the years, if you look at the history of differential geometry, there was an interesting thing that sort of evolved, which was this difference between intrinsic and extrinsic geometry, right? These are very typical terms that we hear a lot, both in the applied domains as well as in theory. Right. So initially, when people thought about geometry, they thought of it as sort of an embedded problem, right? So if we think of the Earth as a sphere, then the Earth is a sort of two-dimensional thing that's sitting in 3D. And based on that perspective, we can derive things like curvature, distances along the surface, and so on by kind of restricting the geometry of 3D space to that two-dimensional surface. And this was the sort of basic construction in classical differential geometry, and certainly goes back to, you know, Gauss and all of the folks back then. But a slightly more recent perspective, I think usually we associate this with Riemann, sort of tries to separate out the intrinsic structure from extrinsic structure. Now, here's what I mean by that. If you take a look at this map on the right-hand side of the slide, this is a map of the world. I think we would all agree that this looks like the Earth. But of course, there's actually two different geometries that are at play. You know, on the one hand, we have a giant rectangle on my computer screen. And on the other hand, we have a map of the world, which is wrapped around roughly a spherical object. And the more that we look at this diagram, the more we can understand that those two geometries are really different. So for instance, you know, I've highlighted two different red line segments, which are the same length. I can tell you, I made them in PowerPoint by copy pasting one onto the other. But of course, we know that these two segments are quite different length if we view them as curves along the surface of the Earth, right? The one that's closer to the equator is probably longer. So this Riemannian geometry perspective, or this intrinsic geometry perspective, says that one way to sort of bridge the gap between the geometry of this rectangle and the geometry of the Earth would be to equip every point on the Earth with some notion of a dot product, right? So the basic idea here is that the ways that you might measure the length of a vector kind of vary based on your position. And that's the sort of basic construction in the Riemannian universe. So essentially, when we're proposing an algorithm for learning from a triangulated surface, what we decided to study was how to learn a Riemannian metric on that domain that sort of facilitates our learning task. So in other words, rather than sort of working directly with coordinates embeddings of the vertices of our mesh, we're going to try to translate that to this Riemannian perspective and then plug that into a set of geometry processing operations that are sort of standard and well understood. So the particular task that we'll consider today is learning features on a triangle mesh. There's sort of two different variations of this problem. One would be a map from the mesh surface to a feature per point on the surface. So for example, in tasks like segmentation, where I want to separate out the ears of the bunny from the face, from the tail, maybe I have a different feature for every point. Or a related, very similar problem will be to come up with one feature per surface, you know, so to distinguish bunnies from, I don't know, furniture or whatever in your computer vision pipeline. This is a standard task in 3D vision, and one that many people on the Zoom call have worked on. And it's also a task that predates the current sort of popular techniques that exist in deep learning. So back in the day, we used to do this by coming up with different clever features involving curvature and triangle mesh processing, maybe heat kernels and so on, and comparing those features directly, rather than the sort of standard deep learning style techniques that we have today. So the question that we want to tackle is whether we can bring those two perspectives a little bit closer to one another. And the substrate by which we're going to do that is the area of spectral geometry. Now, spectral geometry is a very popular approach to shape analysis in the geometry processing community, although it typically isn't necessarily accompanied with learning. Although, of course, that's sort of changed in recent history. You know, things like graph neural networks that are based on the Laplacian operator are quite familiar using very familiar spectral geometry tools. The basic idea of spectral geometry, in case you're unfamiliar with it, is that you can learn quite a bit about a shape by hitting it with a hammer. Now here, when I say hitting it with a hammer, I don't mean hard enough that it shatters, but rather if I tap on a surface and I observe the sound that it makes, you know, so like I tap on that bunny, but I'm not looking at it, then it turns out that just from that audio signal that I hear, I can actually infer a lot of properties of the underlying 3D shape. Now, it turns out fundamentally, I can't infer everything. I can't actually reconstruct a shape from its spectrum. But in the area of spectral geometry, essentially what we do is we use the vibration frequencies and oscillation patterns of a shape to infer information about curvature, you know, embedding maybe, and other things that might be hard to get directly from a set of coordinates. So it turns out that spectral geometry is one of the really standard ways to understand a shape in classical geometry processing. So what you would do is construct its Laplace operator, which is essentially the matrix that kind of governs these oscillatory patterns, compute its eigenvalues and eigenvectors, and then use those as features for whatever your shape analysis task is. Now, a couple of years ago, there was a really interesting research paper which passed by, I guess it would be considered maybe canon or classical in the geometric deep learning world since we move so quickly. But essentially, the basic observation here was that there are so many geometry processing papers that all can be summarized using this green formula, where what you would do is essentially to analyze a shape, you would construct its Laplace operator and then construct a feature per vertex out of the eigenvalues and eigenvectors of that operator. And so what was proposed by Littman and Bronstein back in 2014 was simply to learn this function of the eigenvalues rather than using sort of a prescribed one like the heat kernel or the wave kernel. And this was sort of a really initial attempt at machine learning from shape. And the nice thing is that it really does make sense from a differential geometry perspective, that like there's so many different PDE kernels that are essentially built out of this Laplace operator. All these folks were doing were generalizing a lot of sort of general of popular approaches in geometry processing and applying kind of a light touch machine learning approach to just learning the function of the eigenvalue here. And so really what this was doing is learning a spectral descriptor for shape, in their case for shape correspondence. And when they say spectral, what they mean is that these lambdas here are specifically the eigenvalues of the Laplace operator. So in other words, you compute the vibration frequencies of a shape, you kind of mix them together in a way that your machine learning tool gets to infer from some examples. But at the end of the day, your feature really is constructed from vibration patterns specifically. So if you're thinking of leveraging a particular physical analogy, the physical system here is set. There's nothing being learned about that. What's being learned is what you do with it. So a basic question you might ask is, why is vibration so important? I mean, there's so many different things that I could do to a shape, so many physics problems I could solve and different differential equations that I could kind of set up along the surface. Why do we all study this one operator, which is called the Laplacian, which is giving us vibration frequencies? And if, in case you're not familiar with this style of geometry processing, essentially all it's doing is constructing a matrix whose values are associated with the edges of the mesh. And in particular, they kind of come from the geometry of the surface. So there's a very famous formula called the cotangent Laplacian that almost all of these techniques are based on. But it turns out that many operators in geometry processing and physics can be understood through a pretty basic factorization. That factorization includes not only the Laplacian, but other sort of popular things that essentially are built from partial differential equation kernels, right? So some kind of simulation or analysis problem on a 3D surface, but maybe the stiffness of the problem depends a bit on the particular settings that you care about. And in fact, one of the really interesting constructions in the geometry processing community was this idea of discrete differential geometry built on discrete differential forms. So here, essentially, is a sort of recipe for building up operators like the Laplacian, using particularly frightening notation. But at the end of the day, it actually really is just constructing matrices that look a lot like graph Laplacians. So there's this popular idea of discrete exterior calculus in computer graphics domain, where what you do is if you want to construct an operator like the Laplacian, right? So that operator is basically a vertex by vertex matrix that's built out of one feature per edge on your mesh and one feature per vertex. You can factor it using this slick formula at the bottom of the slide here. So in general, Laplacians are d star plus star d star d. Now, in case you're not familiar with exterior calculus, that's okay. Essentially, the thing to know about this formula is that the D's are combinatorial. They're just encoding like the edges and the faces of your triangle mesh, or in this case, your tet mesh. And then the star operations are basically just diagonal matrices. This might be familiar to you if you know the graph Laplacian formula, where essentially the D would like subtract values along edges of a graph. And then the stars here would be just like edge weights in your graph Laplacian. But now, in addition to having edge weights, you might have vertex weights or per triangle, per tetrahedron, and so on. So essentially what we proposed in our machine learning research was that essentially this factorization here provides a really convenient form for something that we could learn in the machine learning context. And that leads us to this architecture that we called HodgeNet. Now, the basic idea here is that the D operators are combinatorial. They just have to do with the topology of a surface or of a volume rather than the geometry. So somehow those things should be fixed. We don't need to learn those. They're just encoding like the structure of a mesh. And really, the things that we need to learn if we want differentiable spectral analysis of a shape, a mouthful to say, come from learning these star operators. That's actually not such a painful thing to learn, because really all they are local features of a triangle mesh. They just are per edge and per vertex features. So the HodgeNet operator essentially looks something like what I've shown on the slide here. So you input a triangle mesh. Let's say that my task is to like learn a label for every vertex on the mesh. And what comes out, the learnable part of the architecture is highlighted in yellow here. You learn a per vertex feature and a per edge feature, which are like star 0 and star 1, and that Hodge decomposition. And then you can construct a Laplace type operator by just writing that star D formula like I showed on the previous slide. And from here, we just build the rest of our architecture to look like a totally standard computation that I would say dominates the geometry processing literature. So you construct some positive definite matrix, you compute its eigenvalues and eigenvectors, and then compute features out of that. So this last yellow box here really is like that Lippmann and Bronstein paper that I showed you before. So the new modules are on the left-hand side, these star 0 and star 1 per edge features, which are being used to construct a differential operator. So this is a really lightweight machine learning problem, even if we use some heavy-duty math. At the end of the day, what we're learning are just features per edge and per vertex of a mesh that just ingest maybe some information like the coordinates of the local neighborhood and then cook them together into something local. The reason that our features are global and actually tell you something about the entire domain has to do with the fact that we've computed the eigenvalues of our operator later on in this architecture. So at the end of the day, this is actually a pretty straightforward sort of learning architecture. You input the mesh, you use pretty simple machine learning style operations to learn star 0 and star 1 as functions of local features. In fact, just local vertex positions turn out to be enough. And then you compute the features for your mesh by using the eigenvalues and eigenvectors of this matrix L. The nice thing is that every step of this architecture looks like something that a geometry processing researcher from 10, 20 years ago would have done in the days before deep learning. Essentially, the only deep things here are the sort of MLP style layers that we're using to learn star 0 and star 1 from a few local kind of vertex positions. This creates some challenges in bringing the machine learning techniques into this domain. In particular, L here is an extremely large sparse matrix whose non-zero entries are determined by the combinatorics of the triangle mesh. Now, that's a very standard thing to work with in geometry processing, but in deep learning, a little bit less so. And the thing that we really care about are the smallest eigenvectors, like the ones that are closest to zero for this matrix. So hiding inside of this piece of research, what we had to work out was a reasonable way to do backpropagation, which actually does backpropagation through sparse linear algebra. Now, this is a little bit different from many of the graph neural network style architectures where you do like message passing and so on. And the reason why is that we really cared about constructing features out of the smallest eigenvectors of a matrix, which is sort of a fundamentally sparse linear algebra thing to do. But that's not really compatible with this GPU parallel style architecture that's popular in machine learning. So we had to forsake the popular machine learning approach and introduce more insight from geometry processing to come up with a reasonable backpropagation formula. And in fact, at the end of the day, what we found is that CPU-based training of our architecture was equally efficient to the sort of standard GPU things that people often do. So at the end of the day, even if you didn't follow all of the math here, essentially, here's an example of the kinds of things we can learn. So this is a standard mesh segmentation task. The nice thing is that this is actually scaling to triangle meshes that I think were an order of magnitude larger than what you see in a lot of these mesh processing papers. And the reason for that is that we're processing these on the CPU and using sparse linear algebra. So there's never a computation here that scales quadratically in the size of your mesh. And the training time here is still reasonable. So at the end of the day, I think this is a really fun kind of positive example where actually our features are pretty lightweight. They're just local functions of mesh geometry. And every single operation we use here is on the CPU and looks like kind of standard geometry processing, but yet is still achieving state-of-the-art results that are competitive with much more complicated architectures that are using much more specialized style techniques. So in other words, I think there actually is some value in maybe giving up some of the sort of things that we consider to be standard deep learning approaches in favor of what might be more standard in the non-learning geometry processing domain. As usual, I'm talking too much, but I'll quickly share with you a second project here involving a very different shape representation, which is parametric geometry. So in parametric shapes, this is sort of on the opposite end of a lot of different spectrums that come up in the geometry world, right? A triangle mesh is a fairly dense shape representation with a big network of triangles all linked together. In parametric geometry, you tend to have relatively sparse geometry that's constructed out of nice smooth patches that are glued together in a clean way. So learning from parametric geometry or learning to output parametric geometry is quite challenging and in a very different fashion than what you might see in geometry processing for triangle meshes. In particular, we have sparse collections of analytical shapes. They're often linked together into a sort of meaningful and maybe more unique topology. And many of the tasks in this domain actually lack supervision. There are very few labeled data sets, for example, of CAD data, although that's actually changed just in recent history. There's some pretty cool things like this ABC data set, which I think will really change and inspire a lot of fun research. Here's some example tasks for processing this type of data, including vectorization, maybe shape abstraction, sketch-based modeling, and so on. Things where you really care about outputting a smooth shape. So one of the fun high-level themes that we can think about when we work with this kind of shape representation is somehow the transition between Eulerian and Lagrangian geometry. So a lot of times, I think in computer vision, we tend to work with Eulerian style representations, both of shape and other data. And what that means is that we have a big grid and all of the interesting information we have is a signal on top of that grid. So an image is a sort of canonical example of that. Or here I'm showing you like a very abstract, weird version of the level of the letter K, where really this is just a bunch of pixels that are turned on and off. And in a lot of tasks, for example, in vectorization, we might input an Eulerian thing like an image, but we want to output a Lagrangian representation of shapes like a sparse set of curves. Now, Lagrangian representations are like explicit pieces of geometry that are like built out of curves. So rather than having like an underlying grid with a binary value telling me like, is there a shape here or not? We actually have sort of a description of the geometry that's going on. So our early work involved thinking about this transition in a careful way. And what Dima and some of his colleagues at Adobe and I converged on is that a lot of the Lagrangian representations that we have of shape and geometry processing have a really convenient property, which is that we can actually compute in closed form the distance to that shape from sort of a fixed point in 3D. And so what that allows you to do is to actually construct loss functions for our machine learning tasks that kind of look like integrals over space. And so they follow this kind of general abstract form that I'm showing you in green here. And this generalizes a lot of computations that you see, like the chamfer loss, certain types of normal alignment for your surfaces, where essentially what you're doing is maybe integrating over one domain the distance to your parametric shape. So for instance, let's say that I have a task which is supervised where I'm trying to like learn how to place the control points of a parametric curve. Then I need to come up with a loss function, which is telling me how close my parametric curve is, for example, to an underlying image. Then one thing that I can do is leverage the fact that I can compute at any point on the image plane the distance to my parametric geometry to construct a nice loss function. So here's a basic learning pipeline that we could use for tasks like shape abstraction or vectorization. So we're inputting something like an image of a font or a distance field to some shape, something which is Eulerian, like it lives on a grid, and our output is going to be Lagrangian, for example, a vectorization of our geometry. So what we do is use a pretty standard machine learning pipeline for dealing with this grid-based data, which is perfectly fine, in this case, a ResNet. And eventually what we output is a set of predicted primitives or Bezier curves to deal with our shape abstraction problem, right? So for example, if I'm trying to input this letter B here and output a bunch of parametric curves that cover the shape, then eventually I predict a set of Bezier curves and I want to know how well they fit my data. And what I can do is I need to find a way to make these Bezier curves talk to my original data, which lives on a grid. And in order to do that, at every single pixel on my grid, I can compute the distance from that pixel to the Bezier curve in closed form. And this is a differentiable function of the control points. And what that allows me to do is to implement loss functions that measure alignment in a nice differentiable way, where when I move the control points of the shape, I can actually understand the relationship between that and my original data that lives on the pixel grid. And so this allowed us to tackle a number of different tasks, things like abstraction of fonts, like what you see on the left-hand side, coming up with interesting ways to interpolate between data, and then finally, some of those typical kind of 3D shape abstraction tasks. In fact, just this year, coming up at SIGGRAPH Asia, kind of a fun thing happened, which is that this work on geometry processing machine learning actually inspired a new geometry processing method in our group for an interesting geometry processing problem, which is hex meshing, where essentially by using these same nice differentiable operations, but now just built into sort of a classical optimization pipeline, we can do quite well on a geometry task that involves no learning at all. So I'll encourage you to take a look at that paper online for details. But what you'll see is that a lot of the same techniques that we were using for differentiable machine learning actually have some nice bearing on this sort of classical meshing task. So finally, I thought I'd tell you about a fun sort of follow-up paper that we had for studying problems that involve predicting 3D CAD models given some signal or another. In this case, perhaps it's not supervised, and moreover, some of these techniques that we have involving computation on a grid are maybe no longer feasible because we don't want to have to do a bunch of math in 3D involving a volume worth of computations. So for example, here, maybe we're working on sketch-based modeling. So what we want to do is predict a 3D shape given a sketch of some 2D version of the geometry. And we're going to do that in the CAD setting so that we can actually 3D print our model when we're done with all of this. Now, there are a lot of interesting themes when we study these sorts of problems of predicting a 3D model from a 2D image. For one, these problems tend to be self-supervised because it's very hard to find supervised 3D data out there, like CAD models paired with sketches of the same CAD model, I think would not be a realistic assumption for training data. Moreover, there are a lot of interesting topological challenges involving, how to build a shape out of these basic patches. But essentially, one of the fun observations that we can do, similarly to our previous approach. Now, in our previous approach, we took a lot of loss functions and understood them as integrals and quadrature over some underlying grid. In this case, what we observe is that a lot of cost functions for these sort of CAD surface learning problems can be understood as surface integrals. And these are actually nicely compatible with the stochastic gradient descent procedure, so long as we do our quadrature carefully. So what we show is that a lot of different loss functions, which are pretty standard for measuring alignment of our 3D model to some ground truth, can be understood as the integral over some surface. And the way that we end up implementing that is by pulling that integral back to the parameter domain, working with the careful change of variables, and then incorporating it into stochastic gradient descent. So in other words, when we do SGD to learn CAD patches for our prediction task here, we also incorporate into the stochastic aspect of stochastic gradient descent, randomly sampling points in the parameter domain and approximating this integral in an unbiased way by doing our change of variables carefully. At the end of the day, we're able to tackle some fun tasks. So for example, here I show some nice examples where we're able to predict 3D models from 2D hand-drawn sketches, in addition to some of the other kind of fun model tasks that people study, like interpolation in some latent space of geometry, and even some actually quad meshing tasks was a typical kind of problem that we study in the geometry processing domain. So in any event, I probably packed way too much into one set of discussion here, but the basic point that I want to sort of share today is that the classical approaches that we have to geometry are really valuable to think about, even in this learning setting. And in both the mesh and in the parametric geometry setups, by incorporating the insight that we have on how to understand and process 3D shapes, we actually can get state-of-the-art learning architectures with fewer learnable parameters and relatively good performance. And somehow that's quite heartening to a researcher like me, that essentially, by remembering some of the classical ideas that this community has developed over a long period of time, even if we incorporate sort of a light learnable aspect to these problems, we can do quite well. Now, there are many, many directions to go next, everything from, maybe reconsidering the whole geometry processing pipeline in the context of machine learning, from geometric flows to deformation and so on. I think one really important theme is that in geometry processing community, a really important thing that we do is essentially almost all geometry processing algorithms are constructed from sparse linear algebra, and yet, finding the k smallest eigenvectors of a matrix is not a standard operation in deep learning. And I think essentially coming up with very general purpose toolkits for that will help not only our community, but also graph-based learning as well. And also understanding the sort of interaction between the typical approaches in geometry processing and shape representations that are more popular in 3D vision. In any event, I really appreciate everybody's time. As always, I've talked far too much, but I think I have a minute or two to answer any questions you might have. And really, if people have questions, directions for future work, or you just want to chat, you're always welcome to reach out. It's always my pleasure to hear what people are excited about. So thank you so much for the kind invitation today. And I'm more than happy to chat now or later, whatever you all prefer.
Thanks, Justin, for a great talk. I think we have one question from the audience on your first part of the talk. The question is, if instead of the triangle mesh, if you want to learn features on every point in the point cloud using k neighbors, can it be done using the operators that you showed?
Yeah, it's an interesting question. So I think this HodgeNet architecture, one way that you can understand it is that essentially you have this graph Laplacian operator and you're trying to build features out of its smallest eigenvectors and eigenvalues. We're specifically making use of this these Hodge-star operators, which are popular in geometry processing, but you can think of them really as just edge weights in a Laplace operator. And so from that perspective, you might lose some connection to geometric PDE if you don't have a nice underlying kind of triangle mesh structure.
Right.
Like I think it would be hard to talk about convergence, but if you wanted to use the suggestion in the Zoom chat here, I think you could. Essentially what you could do, as our colleague suggests, is build this k-nearest neighbor graph and then probably just learn edge features on that graph based on the point cloud. And then the rest of the architecture would still kind of work okay. In fact, my suggestion for a very low-hanging piece of fruit based on that research paper, essentially we're handing you a differentiable way to learn edge weights on a graph. If you kind of squint at that paper the right way, I think that there's definitely some opportunity to just classical graph machine learning and totally forget the geometry processing aspect using this architecture. And I'd be very curious whether that works well or not. It's been on my to-do list for a while, but it's probably never going to happen. If anybody wants to do that stuff, they should reach out.
I can understand.
I guess
go ahead.
I guess I have follow-up questions on this. Okay, my original question, I really like the HodgeNet or the star operator sounds interesting. But like I really like the Laplacian and using all of these things. So is this what you're suggesting? Which is like, for example, you could have just made all of it into a graph convolutional neural network, which will also learn like the feature on the meshes and also like the edge weights through the network, right? You could still compute all of these, do these eigenanalysis and use that global representation. Is that kind of like what you're suggesting, I guess? Or like, I'm curious, what would the difference be in like using
That's a fabulous question. Let me see if I can deconstruct it a little bit. In fact, the reason, the sort of inspiration for that work was the fact that, like, as a geometry processing person, when I look at some of these graph neural networks, it's somehow they're like mildly uncomfortable to me. And let me tell you why, and then I'll tell you how I think we can connect these things together. So usually in geometric PDE and in geometry, before machine learning, whenever we talk about the Laplace operator and its spectrum, what we care about are its smallest eigenvectors, right? In other words, like if you're computing vibration frequency, it's the low frequencies are typically the ones that are relevant for shape analysis, right? The high frequencies tend to be noise. Not always, but often. Now, if you look at a typical graph neural network, at least, circa 5-10 years ago, these days everything changes so fast, I don't want to overclaim. I mean, what do they do? You can understand them as kind of like multiplying by the Laplace operator on every level, on every layer, right? That's kind of like what message passing is doing in some sense. Obviously, this is a vast overgeneralization. And so when you do that, I think it's easy to compute high frequency information. What's harder to capture is low frequency information, right? So that's sort of what's going on in this architecture, is computing low order eigenvectors. But I think that there's an interesting connection and way to bring these things together. So in the current HodgeNet setup, what we do is we compute these vertex features as literally just a function of the one ring. And similarly, you compute the per edge feature as a function of the sort of two triangles that are adjacent. And the reason is that that's basically just borrowed from how people usually discretize differential equations on a triangle mesh. But it's not clear if that is a bottleneck for learning. So for example, one thing you could do to bridge that gap, as you suggest, would be to maybe use a graph network to learn a feature which is effectively a function of a larger neighborhood, and then use this HodgeNet thing to propagate information over the whole domain. And I think it's really interesting to do that. Like essentially, what worried me about dealing with triangle meshes plus standard graph neural network is that we really care about this idea of convergence and the limit of refinement. Like if you get a finer triangle mesh, your algorithm should behave better. But in a standard graph neural network where every layer you just talk to your neighbors, the denser your mesh is, the sort of less distance information can travel. So the differentiable spectral computation is somehow dealing with that, but it could still easily be that larger neighborhoods for computing those local features is also valuable. So it would be fun to glue these things together for sure.
Oh, this is really interesting. Can you, maybe I don't really get this, the Hodge part, but like, what does it, how does it, because it's really based on this geometry that allows you to have this limit conversion stuff. Yeah, I see.
Yeah. So for example, I mean, the standard operator that we all know and love is the Laplacian. And the Laplacian, the standard formula for it is this cotangent thing, where for every edge you look at the two. I'm making a weird hand gesture. Like if you look at the two angles that are adjacent to that edge and sum together the cotangents, that ends up being like the edge weight in your graph Laplacian. And that formula itself has this nice property that really it's trying to capture the Laplacian of the underlying surface, right? And so what ends up happening is that if you refine your mesh, the eigenvalues and eigenvectors sort of converged under very strong conditions to the sort of right spectrum for the shape. In our case, I don't want to overclaim. HodgeNet is not constructed in a way where you can prove that, like, if you have a finer mesh, you really converge to some underlying spectral problem. But at the very least, we want to use operations that sort of feel like the standard things people do in finite elements, so that's a possibility. So what we found is that plus a little bit of data augmentation. So for example, like when you load your meshes, you can decimate or subdivide during the training procedure. Is a reasonable way to kind of learn those local functions. But there's a lot more to do here, I think, for sure. Yeah.
Let's have one final question. This is a question I also had. So when you're dealing with parametric representations with deep learning approaches, usually standard networks have a predefined set of outputs. So you can only output like a fixed set of patches. If you want to vary that, do you think that's possible, or what would be the possible ways to deal with that?
That's a really great question. And to me, this is one of the big open problems in this space.
Right.
Yeah, that's absolutely right. So the way I would view it is that we all, I mean, in some sense, this entire ICCV workshop is focused on geometry. There's this other thing that we care about in math, which is topology, and that tends to get overlooked. And for good reason. Essentially, we all really like our learning architectures to be built on differentiable stuff. And topology, in some sense, the definition of the area of topology is it's like all of the math that you can't get with a derivative. And so I think all of us are coming up with creative ways around that problem. So for instance, in the work that I showed you with parametric surfaces, what we were able to do was, for a lot of these tasks, like maybe I'm willing to specialize a little bit. So rather than generalized sketch-based modeling, I only do sketch-based modeling for coffee mugs. Then one thing that you can do is, which we show in this paper, is a pretty reasonable, just classical geometry processing style approach to inferring a reasonable set of patches that works across that shape category. But I think what would be really interesting and cool would be to find more sort of learning inspired ways to actually infer both the topology of the shape that you're trying to reconstruct is of course the really hard topology problem. But then beyond that, there's more topology problems than that. So for example, if you're constructing triangle meshes or CAD patches, you need to find the right reasonable layout of those over the surface. And that itself is a challenging topology task. To my knowledge, there are very few algorithms out there for that task, and the ones that are preliminary. There's still a lot more to do before I think we'll see them adopted in industry, for sure. I love that problem. I love to talk about it. I just wish I had a good idea for how to solve it.
Yeah, we'll be happy if you can join us with the discussion at the end of the session, and we can talk more about it. So thanks again for the great talk.
Sorry, Adarsh, I will just like one, I will take the freedom to be an organizer and ask one more thing related to the workshop. So for the, so we talked about two tasks, right? Like one in the 3D geometry inspired deep learning, and the other one in the parametric domain. So for the sake of this workshop, have you tried the 3D approaches on the ABC data set, or have you tried the parametric approach on the skeleton parametric data set?
No, but it sounds like a good thing to try.
Yeah, we are looking forward to your submissions then. Great. So now in the program, thanks again, Justin, for very nice talk. I tried to live tweet your talk a lot, so you will see like 30 tweets that is mentioned in your slides. So just like don't.
Oh, okay. Yikes.
Yeah, so everything is there with my like listening and writing lack of skills. So thanks again. Now in the program we have the poster session, and the poster session is actually happening in Gatherly. So let's leave here, not leave here, don't leave here, stay here, but I will put the Gatherly link in the window so that we can all go and talk with the poster presenters there. So after that, we will have the award ceremony where we will announce the best paper awards, best paper, best student paper, and best challenge paper. So if you are an author in this workshop, you would want to stay for the award ceremony because you may be one of the best paper awardees. And after the award ceremony at 3:50, we will have this open discussion very similar to what we had just right now as a Q&A, but it won't be just for Justin, but it will be for everyone. So organizers will be here. Hopefully, like the keynotes can join us. Hopefully, authors will stay after the award ceremony so that we can have that like collaboration and discussion session where new papers may be seeded, where new use cases for the data sets, or how we can extend the data sets, or what happens for the next version of the workshop, visually, hopefully in CVPR 2022. So stay tuned for those. Join us at 3:50 for that open discussion. Now going to the poster session.
Thanks, Dina. Thanks, okay. And see y'all in some time.
Alfieri, and today I'll be presenting our paper titled Investigating Transformers in the Decomposition of Polygonal Shapes. Hello everyone, thank you for attending my presentation. I am Andrea Alfieri, and today I'll be presenting our paper titled Investigating Transformers in the Decomposition of Polygonal Shapes as Point Collections. Let's start by defining what visual sets are. As we all know, a set is a collection of distinct elements, and visual sets are sets within images. So, for example, the set of objects in an image for the object detection task, the set of points of a polygon for the polygonal shape prediction task, or the set of labels for a single image for the multi-label classification task. Set prediction is difficult for two main reasons. First, because a set has an unknown cardinality, which means that we don't know how many elements the set will contain, but also because a set is permutation invariant by nature, which means that we don't care about the order of the elements within the set. And this is a problem for most deep learning architectures because they often work with tensors of predetermined shape. The architecture we decided to work with was the transformer model, which in particular was the DETR transformer presented in 2020, which is composed by three main modules: the CNN backbone, which extracts a set of image features, and then the transformer encoder and decoder. In particular, the encoder takes the sequence of image features and outputs a sequence of the same length, which is then used as context by the decoder to output the final set. In particular, the transformers can work using two main approaches, the autoregressive approach and the parallel approach. Let's consider the set here at the top, composed by the green, the red, and the purple elements. If we want to predict this set using the parallel approach, what we do is we feed a long sequence at the bottom of the decoder, which is then transformed into a sequence of the same length. But as you can see, this sequence is much larger than the actual cardinality of the set we're trying to predict. And this is because the parallel approach uses the oversampling technique, which means, again, that we predict more elements than necessary and then discard the excess. On the other hand, we have the autoregressive solution, which is able to directly predict the correct cardinality of the set. And it does so by predicting each element of the set one by one, autoregressively, by conditioning each prediction on the previous ones. So as you can see, in this case, we are predicting the purple element first, and then purple is used to predict green, and then purple and green are used to predict red. What we know from previous work is three main things. First, we know that the attention mechanism can work quite well on set prediction tasks. We then know that the parallel transformers was never able to achieve state-of-the-art results on pure sequential tasks, such as the machine translation task. But we also know that the parallel transformer was successfully used to solve pure set prediction problems, such as object detection or panoptic segmentation. Our contribution is then twofold. First, we demonstrate that the presence of a natural order is a strong discriminative factor for parallel and autoregressive transformers. And we then study and provide evidence upon important properties of these two models, mainly their generalization capability, their strength against small data set, or the importance of the impulse orderings for the autoregressive solution. Why is it important to study upon this? Mainly because the oversampling technique is wasting a lot of computational power. And this is because the attention layer has a computational complexity of n squared with respect to the sequence length. So you can see clearly if we are using 100 objects, 100 element, a sequence of 100 elements when our images contain 5 or 6 objects, there's a lot of power going into waste. And this also comes from the fact that the parallel approach is using an algorithm called the Hungarian matching algorithm, which has a computational complexity of n to the power of 3 in its worst case scenario. So what we've done was we developed a custom toy setting dataset where each dataset could help us answer very specific questions. The first two datasets we implemented were the line toy setting dataset and the points toy setting dataset. At the top here, you can see the line toy setting dataset, which is a dataset of images, of black and white images containing a single line composed by multiple segments. And the task here was to predict each point of the line following the natural order of going from the bottom left to the top right of the image. At the bottom, you can see the points toy setting dataset, which is a dataset of images containing just points, where the task was to predict all the points of the image in any order. So you can see that the main difference between these two models is that the presence of a natural order in the predictions. On the left, you can see the results on the line toy setting dataset. As you can see, as the threshold remains large, both models perform comparably, but as this threshold becomes smaller and smaller, and we require our predictions to be more precise, then the parallel approach quickly drops in performance and cannot detect any point of the line when the threshold is smaller than 0.05. On the right, we can see the results on the point toy setting dataset, and as you can see, these are reversed with respect to the previous ones, because if the number of points per image remains low, then both models perform comparably, but as this number grows large, then the autoregressive solution quickly drops in performance. The next dataset we implemented was the gates toy setting dataset, which are images containing polygons of 4 corners, which we call gates. The reason why we implemented this dataset was to validate our previous results on a dataset that is closer to real-life tasks. But also we use this dataset to study upon the generalization capabilities of these models. These are the first results we collected. As you can see, these are very similar to the points toy setting dataset results, because as the number of gates per image remains limited, then the autoregressive solution performs comparably to the parallel one. But as this number grows larger and larger, then the autoregressive solution quickly drops in performance. Instead, these are the results for the generalization capabilities of our models. And for these results, we trained our models on images with 1 to 5 gates and tested them on images with a very specific number of gates. As you can see, as the cardinality remains between 1 and 5, both models perform comparably. But as this cardinality grows larger than the maximal cardinality seen during training, then the autoregressive solution quickly drops in performance, which shows that the parallel one is has a greater generalization capability to unseen cardinalities. The next dataset was the real gates dataset, and these are real images of gates. To be precise, these are generated using a graphical engine. And as you can see, there's different scenes in these images where the walls are different, the ceilings, the floors, the light can come from the outside or the inside of the scene. And we've decided to use this dataset first to test what happens on real images, but also to test how our models behave when the data availability is limited. These are the results, and as you can see, we've decided to compare against a strong baseline such as MaskRCNN, and the parallel approach was able to outperform MaskRCNN on both the gates toy setting and the real gates dataset. But this comes at a training time that is almost double the one of the autoregressive solution. We then studied the most important properties of the autoregressive approach, mainly the use of positional encodings and the different orders that we can impose on the predictions. And as you can see, the best results were always collected by not using the positional encodings and by basing our order on the position of the polygons in the image. The last dataset we implemented was the polygons toy setting dataset, which is a dataset of images containing any amount of polygons. And now the problem becomes more difficult because each element of the set is a set itself. And this is because each image can have n polygons, but also each polygon can have different amount of corners. To solve this problem, we decided to implement a custom solution where we treat polygons similarly to how NLP treats sequences of words. And let's consider, for example, an image containing the green and the green triangle and the blue square. The target sequence for this prediction will be composed by the special start and end token at the beginning and at the end of the sequence. And inside the sequence, we will predict the points of each polygon followed by the special end of polygon token. Using this solution, we show that the autoregressive approach outperforms the parallel one without increasing its training time. And we believe this to be caused by the greater capability of the autoregressive solution to work on smaller tasks. In conclusion, we've shown once and for all that the presence of a network order is indeed a strong discriminative factor for these two models. We've shown that the parallel approach is preferable for pure set prediction problems, but that the autoregressive one is still a viable solution when the set cardinality remains bounded, remains limited. We've shown that the parallel approach has a greater generalization capability, and we've shown that complex elements can be successfully decomposed by the autoregressive solution. Thank you for your time.
All right. Sorry, I don't know whether people can hear me, but hopefully you guys saw the talk well. I don't know if the authors of the talk are in the Zoom. Looks like they're not here. If you have any questions with the talk, please feel free to contact the authors directly, and hopefully they will respond back. We have 5 minutes, so in 5 minutes we'll have the awards presentation and followed by the discussion, a general discussion on geometric deep learning. So let's just wait for 5 minutes, and then Ilke will come back and talk about the awards.
Okay, we are here for the award ceremony. Hopefully the authors and everyone that did some presentation today, either in orals or posters or spotlights, are also here. I don't see some of them, but I can understand that like this is not a very friendly time maybe for people in Europe and other parts. So hopefully they are here. If they are not here, we will try to reach them via email and other things. So are we ready for the award ceremony? I know it is the end of the workshop, kind of like not the end, but like we had the like loaded schedule. So okay, everyone can hear me? Just checking. Okay. Everyone's like, okay, cool. So yeah, it was like a loaded schedule. I know we may have a little bit less energy than normal, but let's have this award ceremony, and hopefully it will at least cheer up us, right? So we will first go with the best student paper. Can I have a drum roll? Everyone does their own drum roll, okay? So the best student paper for, and I cannot switch to slides, that's fine. Okay, the best student paper for our workshop goes to Andrea Alfieri, Yang Kong Lin, and John C. Van Gemert. I'm sorry if I'm pronouncing all the names wrong, but doing my best, with their paper called Investigating Transformers in the Decomposition of Polygonal Shapes as Point Collections, which is just being presented, right? Like it was a nice coincidence that the first award goes to them. So thanks for submitting to our workshop. We really enjoyed, like the reviewers liked the paper. And I think it's a nice merge of like transformers with the point collections. And we really look forward to see the next step of that, with like going beyond toy data sets and like having like real world examples and running the experiments on these data sets. So congratulations. Is any of the authors here? Any of the authors of this paper? I wish they were here. There is someone on the Zoom which is connecting with audio right now, so I'm hoping maybe they are one of the papers, because I don't know the abbreviations of their names, but okay. Going for once. No, this award is already gone. So anyway, okay. So let's continue. So the next paper, workshop award will be the best paper award. And let's get another drum roll going on. Are we ready? I wish this was in person. This is not really like creating that tension, like who, right? Okay, anyway. So the best paper award goes to Shyam Taylor, Rene De Jong, Tiago Azevedo, Matthew Matina, and Partha Maji, by their paper towards efficient point cloud graph neural networks through architectural simplification. And this, we also saw this presentation today. It was a nice presentation and nice theoretical hypothesis that is proposed by the paper, saying that like, is this like really the first layers, really the feature extractors are more important, so we should focus on them, and we need to like, we can focus less on the other layers. And they did nice experiments to actually prove that, not prove, but like support that hypothesis. So this was a really good paper, and I think it has very nice insights if you read the paper. And we hope that this will be useful not only for the listed authors, but for all of us when we are processing point clouds in a deep learning setting. So any of the authors are here, hopefully? I remember seeing Sam somewhere during the day, during the presentation for the Q&A. Maybe they didn't stay for the paper awards, but anyone? Any of the authors? Maybe we should have given spoilers to them so that they would stay, right? This is like completely just within the reviewers and the PC, the awards, and we didn't inform any of the authors about anything. We wanted it to be a complete surprise. So anyways, but congratulations, Shyam et al. For their best paper award. So the next paper, the next award. Hey.
So the author for the best student paper was on YouTube.
Oh, okay, really? I'm sorry, I did not.
That's in the chat.
Okay, the one place that I was not.
And he seems to be happy.
Is it Yang? Oh, Yanko? Oh, Yanko is here right now. Hey, Yanko, congratulations. If you want to say a few words, you can say. Let's go to your slide. I see you in the Zoom if you want to talk.
Yeah, we're glad to get the prize, many surprise. I didn't expect this actually. So anyway, thank you very much.
Great, thanks for coming. Congratulations. And again, as I said, maybe you heard from YouTube that we are looking forward to your experiments in further data sets. So okay. Okay, calling for once again for any of the authors in the best paper. None. Okay, I will continue. So the last drum roll for the best challenge paper. Are you ready? The best challenge paper goes to Priya Kansal and Sabari Nathan for Skeleton Net version 2, advanced channel attention blocks for skeleton extraction. And we have seen the presentation. We have seen the presentation in the morning, and we have seen their really nice results on point clouds and pixels, and how those deep learning approaches can be generalized to different domains that are also in the skeleton dataset. So we congratulate them. Is any of the authors here? Priya or Sabari? I remember seeing Priya in the morning, but I haven't seen now. Hey, Justin. I wish we could also give you an award, but we were waiting for no, but I was expecting to see the authors of the award winners. Okay, anyways, let's continue, and congratulations to Priya and Sabari. And actually we have one more surprise for you. So since this is the best challenge paper and it had the highest reviews as the paper reviewers, and we believe that you need more power to actually run your experiments on our data set. So we congratulate them, and we also want to award them with an NVIDIA GPU as the best challenge paper. So congratulations, we will contact you about how this will work. And we will also send the some actual physical certificates to all of the award winners, and I will email you about your address, etc. So we can do that. If you don't want to give the address, we can email you and or a digital copy too. So we can handle that later. So thank you. So let's actually so maybe I should call one last time any of the awardees for best challenge and best paper here. No. Okay, I continue. So that is actually a nice transition to our discussion and collaboration session. So I just put some questions there. That we don't need to like answer any of them specifically, but I hope these will be a little bit like opening like icebreaker questions about like why you are here, right? Like that's the essential question. Like what did you take away overall from the workshop, or what surprised you, or what intrigued your interest, or have you worked on any of the data sets that we have been talking since the morning, right? Or do you have any like future projections about the, deep learning for geometric computing, or what are the current gaps, or as from the Q&A from Justin's keynote, what are the low-hanging fruits maybe we can work together, or like you want to work next, or if you have any questions to any of the authors, any of the organizers, any of the keynotes, anyone. So I will give this introduction and leave the rest to you. By the way, I want to add one more thing. I'm really sorry. So I want to add a special thank to Shivanand and Sharjeel for being here as the participants that attended the whole day and most of the whole day, and everyone that stayed through the whole day. Thanks a lot, and hopefully now this is the time for all of us. Like there is no labels anymore right now. So we'll all just have that free conversation that can hopefully enable all of us work together in future. Yes, there are some chats. You can just join, like just like jump or raise your hand or do something. I see new faces, like not new, but like Bernard, welcome. Thanks for spending time on a Saturday. I know you are very busy, but thanks for coming. So yeah, the stage is yours.
Yeah, I think the talks were very inspiring today, and we saw twice the same question coming in this keynote talk about the 3D representation you should use in Nilois Mitra's talk, and in Justin Solomon he also said like should we try to mimic and go to the image processing people because they have been doing neural network very efficiently, or should we try to do something that is more specific to 3D? And I think, yeah, that's probably something that will, some question that will remain for the coming years on this balance between being specific to 3D or benefiting from all the work that has been done in 2D, I guess.
I think it's an interesting point. I mean, if you look at a lot of the techniques that we have right now for 3D, specifically with machine learning, I mean, I think they follow a totally reasonable path, which is, you know, we have these successful algorithms for 3D vision, largely based on image processing. And so, you know, from a research perspective, it makes perfect sense to sort of say like, well, you know, given the success there, what can we learn and transfer to our domain? On the other hand, I think a really compelling question to ask is like, if we didn't know any of that stuff exists, how would we go about engineering a machine learning pipeline? And my guess is that it would look a lot different from what we have today. Does that necessarily mean that it's better? No. I mean, maybe there's something magic about, you know, convolution and neural networks and layers and so on. They're just not things that are familiar in the geometry world. And I think we haven't really addressed in a careful way precisely what the interface looks like. Yeah, so anyway, I don't have a well-formed thought, but I think it's definitely something that's worth thinking about.
Yeah, and maybe there is also something about dimension. I mean, just because I'm biased towards the Skeleton challenge, but yeah, in 3D things has been going like surface representation is mostly the most classical thing, but we have been seeing a lot of volumetric data coming in and volumetric meshes and so on. And on the other hand, the skeleton are a way to lower the dimension and not to make it higher. So maybe there is also some interplay or something to play with this change in dimension, or so. I don't know. just also not not very structured ideas, but maybe there is something to gain there, looking at lower dimensional representations.
Maybe one thing that I was thinking, probably intrigued by Anju's talk, is that sometimes especially in 3D, we are trying to balance the regularity of the overall like space subdivision versus like not doing anything about it and trying to process it from everywhere, right? Like there's as if like there's only features and there's no spatial subdivision, etc. So maybe I was thinking that like there is like some balance in between where you can still actually learn things without like spatial constraint, but still in a subdivided way, like the plan of trees, right? In a way that like it's still is a little bit closer to conventionally what we have been using, like for voxels or like, I don't know, octrees, KD trees, etc. And whether like inside, like, for example, the spherical harmonics, right? Can we do something domain specific there? So instead of using like a general spherical harmonics as the basis, like as if, for example, if we are going to the tree representation, maybe there is like a better span for the tree branch minimum units, so that instead of learning the spherical harmonics, we are using that like minimum branch representation, for example, and that is still like as parameterized in a way that can be applied to the learning setting, for example. So that was some ideas that was like passing while I was listening. So if anyone has work on that or ideas. I don't like the silence, so I will. Maybe you are thinking though. That's completely fine. But maybe I will go to my list of cheating questions here. So if you can pick one topic from this workshop, like not on the general level of sure, deep learning for geometric computing, but like one specific topic from this workshop, what would you like to work on? Or incorporating your research? And I know we are like researchers in this area anyways, but like maybe one novel thing or novel dimension that you want to experiment, or like one, like I can apply this to that, which is not done before, something like that. You don't need to disclose your next paper, but I'm just like asking, general way.
I wanted to get back to what Justin was telling about, like the topology and geometry issue. I think to me that was the one thing I still think would be like a fundamental but really cool problem to tackle if we can tackle it in the first place. Maybe we can, Justin, you can talk a little bit or your thoughts on it.
Yeah, there's some recent works in other branches of machine learning where they're trying to figure out how to learn combinatorial structures, right? Some of these different tricks for making combinatorial problems differentiable, like these stochastic softmax tricks, I think is one of the popular approaches among many others. I think in terms of in this particular domain, I think it's really tricky. I think it requires a pretty substantial departure from the approaches that you're seeing right now, right? I mean, right now are a lot of these, in some sense, maybe it'll force us to think about approaching geometry problems in a way that really doesn't look like a CNN, because this is just not a problem that appears in that universe. In fact, I would be kind of hard pressed to come up with the right analog in image processing for these sort of things. I guess maybe some graph inference problems are kind of similar.
Right.
But yeah, I don't know, making these problems differentiable or coming up with machine learning techniques that simply don't depend on that is wildly challenging. Yeah. There's some interesting approaches out there to try and make topology differentiable as well. I know, like in the topological data analysis community, you know, like there's some differentiable versions of persistence diagrams and so on. I don't know how easily those translate to the types of settings that we've heard about today, where somehow you have to make a hard and fast decision about your, you know, like in some sense, topological data analysis is all about the sort of making some fuzzy style inference about topology, but like if you're trying to actually construct a surface, you don't have that luxury. Like you actually have to glue stuff together. So I don't know how relevant that'll end up being.
Yeah.
You know.
I certainly agree. And maybe one more comment, not on the idea space, but on the collaboration space. We, as I mentioned in the very beginning of the workshop, we have a research network called WISH under AWM. And in that one, we are trying to explore both the topological and geometric features of shapes, general shapes, 2D, 3D, where Skeleton came from, where Geraldine is like one of the leading people here. We have Catherine, one of the organizers, which is also like, she's like the guardian angel that all of us look up for. If you want to like collaborate with us or like join the next WISH, which is hopefully in 2 years and in person, hopefully, just like you can reach us, you can like talk with us. That is like Skeleton seeded from there, and many other collaborations seeded from there. And I think it like the current projects that we are working on there are really like very relevant to the topic, and hopefully they will see the light of the day in the next conference, and in that case we will say that, oh, this came from WISH. And anyway, so I just wanted to say that like there are like research networks that are working on those problems. So.
Sorry, excuse me. I got 2 questions. I'm not sure whether, okay. Anyway, so nowadays we see a lot of huge interest in deep learning. So, but like in the past few decades, we have been working on those old school like image processing things. But now it seems like people all do away with those old school things. So, do we see any opportunity for those old school things in deep learning era?
Can you give us
all hope.
example? Can you give a specific example? Like you're saying, like how old school things are being used with new deep learning techniques? Is that what your question is?
Okay, so for example, there is like a very fundamental task in computer vision or image processing, line segment detection. Like we want to detect those 3 lines. Like 50 years ago, we have half transform, all kind of like simple techniques. But nowadays, I see people using like huge or fancy deep neural network to this kind of task. So like, I mean, those are very simple, like low level features. We would expect some like super fast implementations, but now a huge networks, it takes like at least a GPU, right? So, I mean, it's something good, or like, I feel a bit sad like for those old school people. So like those are really some nice knowledge we have been studying in the past few like 20 or 30 years. So like suddenly everything is gone. So it makes a bit sad. So
yeah.
I think there's a big effort recently for people to kind of reconsider some of those classical techniques and maybe apply a perspective that, from my perspective as a math person, I think of it similar to optimal control. You know, like somehow, like if I know how to solve a differential equation, I don't need to make a learning tool that solves differential equation. but I might want to make a learning tool that incorporates my solver and then learns boundary conditions to get a desired effect. And somehow I think you see that a lot in vision, you know, like as you say, maybe Huff Transform does exactly what you want for detecting edges, but now you want to differentiate through it to learn some higher level thing that might be harder or incorporate some inference from data. And I think you see a big push in that direction. I mean, it's kind of funny, like 5-10 years ago, I would have totally agreed with you that like somehow everybody is ignoring the classics and you know, rediscovering basic computer vision by neural networks. I think these days it seems like there's a trend to incorporate some of these basic techniques just within a learning architecture, and I think you see that a lot reflected when people talk about, you know, differentiable algorithms, essentially, you know, like taking solutions to problems we already know and differentiating through them to solve some higher level control task. And that seems to be one of the sort of prominent approaches we see in a lot of domains. I think you could argue that a lot of the algorithms you've seen today are incorporating some domain knowledge, whether it's like rendering or spectral geometry, whatever. And rather than just relying on your neural network to do all of that end to end, or incorporating that and differentiating through it so that you can learn the interesting part. So as always, you know, there's this push-pull between these two sides. They go back and forth, you know. A long time ago in vision, we were all coming up with sort of bespoke algorithms for individual tasks. Then people got excited about learning and we're throwing data at everything. And now maybe there's a bit of a return to some of the older school stuff and not totally neglecting the domain knowledge that people develop. So we'll see. You know, it's I think we're at a really interesting crossroads where the question is, you know, what things need to be learned? You know, are there some fundamental problems that just have solutions out there we should incorporate? But still, you know, the distribution of data can give some insight. You know, there's lots of things that are in that space in between.
I think I really like your question, and I would like to push this question further because yeah, I've been a department chair and I'm in my last year now, so maybe I'm a little biased, but it also comes to what should we teach to the to the coming students, right? Do we decide to just teach learning and they'll be able to have learning algorithms that solves everything, or do we need to also keep teaching these kind of old techniques because at some point they also come into the system and into play? And I think yeah, we know the techniques and we maybe want to use them or maybe not, and that's the question. But what do we what do we give or what do we process to the next generation? And yeah, do they need this basic knowledge or they don't need it anymore? Kind of. I think it's really a nice question that you raised.
I think there was something also in the talk of Andrew. She just mentioned something about the Planock tree that like she was also went to this kind of old algorithm when she was just teaching, and then she could incorporate also this algorithm for her work. So I think it was nice also. I don't know if you noticed, she mentioned that also in her talk.
Yeah, I like that talk very much because like it's very simple interpretation of nerve, like using those vertical harmonics. So it's really mind refreshing. So I would say that's the most interesting part of this workshop. Really excellent. Many appreciations, many thanks.
Yeah, it was also nice that she mentioned, like, I mean, this algorithms that was like, I mean, they made in like, I think 17s or like many years ago, but she just went through them deeply because she was into teaching, and then she inspired, and then she used that for like some very like novel new work. So like, it's always nice to just inspire from like very old algorithm and incorporate it with the new things because they always have this kind of advantage.
So now it seems like what's old is new now.
Yeah, I mean, I agree. Like even as Jason was saying, some of these differentiable rendering and these new ideas which are coming out, they are coming with a flavor of using lesser amount of data. So as soon as, I mean, if you want to use just deep learning and solve for these problems, then you need a lot of data to learn some of these tasks. And also, instead of using the data, you're using some of these old school techniques, if you will, which have been there for us with us for a while. And instead of doing it on like using data collection and all, you're now using differentiable frameworks to actually reduce the data collection, and you're now bringing everything into place. So it's now falling in some sense or the other, falling into place where you're understanding that data is not the only solution to your problem. You need to integrate data with whatever prior knowledge you have and somehow integrate all of them together to come up with a better model, because obviously you don't want to learn a machine learning model to learn some of the things which you trivially know. You want the machine learning models to learn something which you don't know, and you want it to learn in a better way. If you learn whatever is already known in terms of some mathematical tools which you already have, then there's no use of that kind of a model, right? So that kind of, I mean, that's my opinion on this part. Yeah.
And nowadays, like we are seeing the merging, right? Like we see all old algorithms, all like things that we learned, as you said, like years ago, like, and there's like deep in the beginning, right? Like deep marching cubes, deep Poisson reconstruction, deep whatever your favorite 3D or 2D algorithm is, right? So maybe now we are seeing that they are actually merging in a way that I'm not sure whether they are doing better what they used to do better in general, but probably they are more efficient than how they used to be, right? In most of the cases, hopefully. So maybe like a general thing is like, you know, that someone, I don't remember who said, but like machine learning is like a hammer and everyone is trying to find a nail to do that, etc. But I think if the nail is already in the wall, why are we like pulling it back and trying with another hammer, right? So we don't need to do that, I guess. And in that case, maybe like finding like more like how can we do it in a steel wall, or like is the nail actually a rigid nail? So like those improvements and those like future things that they are more applicable to deep learning setting, like in terms of performance, scalability, etc. Maybe we weren't able to do it for all the meshes in the world because, like, I don't know, the manifoldness, the junctions, etc., etc. Now with deep learning, maybe the formulation change and they are more flexible, more robust, more something, right? And then they are applicable. But if they are not applicable, and if they are already doing what we were doing with traditional approaches, then I always say that, like, why the traditional approach doesn't work, why we cannot apply it, then look for the deep learning variations.
One thing I think also is troublesome for me in the deep learning approach is that before we used to look for techniques where you had some approximation guarantees on what you get, for example, and that's something that is missing also in the learning world, kind of so far. Is that, yeah, we compute stuff and it's very efficient and it's compared to ground truth, but yeah, can we get something up to a Hausdorff distance to the original model or something like that? And that's still not here yet. So but thanks for the very interesting discussion. It's very nice.
Yeah, that's a really good talk, Geraldine. Like the topic, like that comes back to the CAD models and topology discussion too, I believe, in the sense that, like, what you want is like a watertight CAD model, and I don't know if there are guarantees that the neural network can provide that essentially gives you like a watertight model in the first place, or building that in might be something that would be really useful in some cases. So that those kinds of guarantees or topological guarantees are also something that could be really useful to build in.
I think, I mean, that problem is more acute when we look at generative problems where you're generating 3D designs and ensuring that those 3D designs make sense. Not avoiding, even if you're not doing like a proper CAD model with all topology, but even if you're using like a triangular mesh and you're generating these triangular meshes, ensuring some of the topological properties, like it should not have self-intersections and all these kinds of tricks. This is itself a problem not well solved in my understanding. So yeah, I mean, that itself is a interesting thing to look at.
I would say even in the traditional generative models, that is not solved. Like if you have a procedural model, for example, and you are trying to generate something, you may forget, I don't know, the far cousins, attachment of the far cousins in the tree, or like you have something that is repeating a lot and that is not realistic. And like you as a technical person see that it is possible because the rule is like that, but the user doesn't see it like that. So even in the generative case, I would say that is not solved for traditional approaches yet. In deep learning setting where the features are not really that interpretable, the rules are not that much interpretable, etc. It is like even harder to actually guarantee that the structure is not broken, the topology is that the rules are like as expected, etc. So yeah, I completely agree. Yeah.
Some of the recent works on like some connected components and using Voronoi cells and all have been something really interesting, where they're bringing some shape constraints in the generative model space, but I haven't seen many works in that area, but a couple of them I have seen, I think from Google or some groups, I don't remember exactly right now, but yeah, some of the works are very interesting in that area.
Right. So they are mostly beginning to be there for the geometry, but tying that the geometric constraints with the topological constraints are not really interlinked at all in any research. Like, and that's one of the topics that we are trying to tackle in our group. Yeah.
Another question pops in my mind. What about those non-differentiable operations like ranking or clustering? So like nowadays, I see the only solution is to like develop some kind of approximation using gradient, like using some differentiable functions. So is that the only solution, or we can do something else? Because training neural networks depends on like gradient back propagation. But what if those operations are non-differentiable?
It's a good point. I mean, I think there are a number of efforts these days, like in differentiable sorting and differentiable this and differentiable that. But the reality is that you can make them differentiable by softening these problems. It's not clear that the derivatives are terribly meaningful. Our group's experience has been kind of not so great using a lot of these tools for the kinds of problems that we're tackling in geometry processing. I think maybe for very small combinatorial problems where even if you had to enumerate all the possibilities, it would be kind of okay. These things can work. But I think there remain a lot of challenges. I mean, the reality is, you can do anything you want to a non-differentiable problem and it'll stay not differentiable. Like there's only so much you can do. And so some of these efforts, in fact, I think even mathematically, it's not super clear what the derivative is telling you in terms of like, I mean, you could even like put on your complexity theory hat, like, should I be using these tools to like sort a list of numbers? I don't know. We'll see. I mean, sometimes you get lucky, right? For example, sorting is linked to some constructions in optimal transport. And so some people in that community have had some nice success with making that differentiable. Other combinatorial problems, less so. So for example, over the summer, we were playing with trying to incorporate like minimum spanning tree style calculation into a neural network. And there, it's not really equivalent to a nice small convex problem, it turns out. So following the usual path to a differentiable relaxation just doesn't work. I don't know. Yeah, we'll see. There are also some really cool efforts where you get around the non-differentiability in a different way, which is using sampling and probability, right? So you look at like distributions over spanning trees rather than computing the optimal one. And in that case, you're sort of not relaxing the object you're trying to compute, but rather relaxing that you have a single decision that your neural network has to make is a different way to incorporate a derivative. And I've always found that to be a really intriguing direction. I'm kind of hoping that that community continues to do cool stuff. So I don't know, it remains to be seen. There's a lot to do here for sure.
I mean, currently the mentality is that like, okay, there is something I want to do. Let's first look at if there is such a differentiable layers or functions or modules in PyTorch. Otherwise, probably we have to find another alternative. So like, so I just don't know, like, it seems like everything in my mind is just deep learning. Okay, some CNN layers and then what? Oh, no, I don't know. Okay, let's maybe collect more data. So that's it. So,
well, the community aspect aside, I think if you're looking for a good way to inspire some research projects, one thing that so part of that HodgeNet paper that I presented, part of the reason why that came into being, because I wanted a project in deep learning that got me writing code in that space. And of course, at the end of the day, that paper basically is proposing a way around most of the things that are in PyTorch, right? Like we work out our own derivative formulas and don't use their modules at all. And the kind of interesting thing that I learned was that if you have the kind of expertise where you can do that sort of calculation, there's a lot of room for you to do research that maybe the less creative folks who want to only work in the modules that exist in PyTorch are stuck working on, you know, like it's somehow a little bit more liberating. For instance, that, like, to be very concrete, like that derivative formula that I showed in my talk was one that like is totally obvious from a geometry perspective, but like people in PyTorch would be really averse to coding it because it would require making your own differentiable module and working through all the formulas and stuff. So anyway, I think rather than being turned off by that, I would view it as a good challenge. Like, okay, so you've got this cool expertise that apparently people aren't using. How could you incorporate it into the pipelines that they're engineering?
yes, totally agree. Like 2 years ago, I started my PD. At that moment, I was thinking, oh, we have CNs. That's everything. Let's do some fancy tasks, cool networks. That's it, papers. But nowadays, it seems like, okay, there are still many challenges we have to tackle. So, yeah. Anyway, thanks.
Okay, another cheat sheet question. So where do you see deep learning for geometric computing in 5 years? Do we understand all the 3D geometry with the topology and geometry and the like visual features and the spectra and everything? There is just like one big network that is explaining everything, and not in only like the in the analysis space, but also in the synthesis space, for example. Can we just like generate whatever structure we want with the underlying properties that we want in a fully controllable manner in an expressive way? How do we tie it to other fields, like with NLP or like with I don't know, the interactive graphics way? Like, what do you see in 5 years? What will we be discussing in 5 years of this workshop?
I would say maybe it's better to add some kind of inductive priors into neural networks, such that solution space are constrained. And I would say this makes neural networks more interpretable. So like for certain tasks, I would say, okay, maybe for lines, we add Hopf transform in a network, and then we can realize feature in Hopf space because the bin is line. So then in that case, it would be, let's say, we can simply identify those bin. Okay, this bin has high intensity, then that's a line. And also we know the parameterization of lines. So I would say, okay, adding knowledge. So not learning everything from data completely. Of course, this would be trade-off between like learning and the classic techniques. So like, there's always this kind of discussion between the industry or academia, so or whatever.
Yeah, one thing I always find is the lack of connection between like the graphics geometry people and the CAD geometry people. So like the CAD people, we love splines and NURBS, which are not that popular with the geometry or the graphics community in some sense. Like most of the time it's just triangle meshes in that side. So that would be something like bridging that gap, I think would be something that should happen in the 5 years.
Yeah, I completely agree. And actually, we have a large part of those people a part of our workshop, but they are actually like most of the ABC people are actually in Moscow, and it's really late there probably. So they are not here in the discussion session. Sebastian is actually here. Maybe he can give more information about that. And we want to yeah, I completely agree with others. We want to actually foster that collaboration and connection more.
My prediction for the next 5 years will probably be that we get rid of the deep part in the name of the workshop. Because if you look at networks like NERF, for example, those are only 8 layers. I mean, for a 10, 20-year perspective, 8 layers are a lot. But from a really deep learning perspective, 8 layers are not that much. And there is other exciting work out there that is only like 2, 3, 4 layers. So it looks like the networks are getting less deep. And yeah, I definitely agree that putting domain knowledge in there will help a lot.
My personal hope is that we bring these tools a little closer to applications people care about. I think a lot of the geometry papers, including my own, we have a tendency to kind of invent problems and then solve them. For example, in the graphics papers, I mean, how many people have analyzed the same data sets of like furniture? I think, the reality is that there's industry demand out there for some pretty practical geometry tools for modeling, for, scene understanding and some other tasks. And I think a question that's not super clear to me is how close the tools that we have in academia really are to penetrating the market. And that there's some really meaningful and deep in the academic sense questions to answer at that interface, that like, we don't need terribly complicated applications to have really challenging problems that are still unsolved. So I don't know, that's what I'm hoping this field will kind of move toward, is thinking about, not just like what's the hardest learning problem we can solve and what data, or like given the data set I have on hand, what learning problem can I solve? But rather, trying to go out there and interface a little more. And this includes myself with people in areas, whether it's medical imaging or computer-aided design or 3D modeling or autonomous driving, whatever, and try to really understand in detail what challenges they're facing and why they're not adopting some of the tools that we've been proposing. In some cases, they are. So anyway, I think there's a lot more to be done at that interface, and we might find that it's even just the sort of the simple tools that turn out to be the most important. So we'll see.
I can't agree more to that. So for example, like even the data sets that we have in the studio, so we run PointNet, for example, on ShapeNet, right? Like cute little data set. But the actual point clouds that we have in the studio are like millions of point clouds per frame. Then we have it for every frame, and the actual like VR movie is like, I don't know, like 5 minutes or more. And in that case, like all of those networks that are very nicely fine-tuned for small data sets are actually not really that effective. So we need to, it's not really incremental, but actually find more ways to process that data in a way that like it is both scalable and generalizable to different contexts and the different like data sets and different even different styles, like that the movie is being like shot, right? So like I can say that like maybe like the studio is the most commercial, like most industrialized way of those shape problems. But like even in there, like there's actually a huge gap of what is actually applicable, like taking from a prototype standpoint on a small data set to that actual production setting where we can apply it to like all the frames, everything in the movie, etc. So we need to like do so many things on top of that to actually apply like a point net plus derivative as a point cloud cleaning method for a real like VR movie that's that premieres in the Venice Film Festival, for example. So I completely agree that like there is like a really gap in between, like even if you compare the input, like the actual input to the system, right? Like most of the multi-view systems that we explore in academia are like, yeah, sure, like couple of views with like couple of gigabytes, right? Like storage is almost never a problem. Maybe sometimes we have 270 gigabytes coming, like per second. Like how do you even actually, you can't store all of them. How do you even pre-process to actually go to that volumetric reconstruction at the end so that you don't actually lose data, etc. So I think sometimes like we have even more basic problems because of the amount of data in the industry and amount of context in the industry that we can't even go to the actual like the deep part, right? So I really agree that like in 5 years or 10 years maybe, or maybe sooner, hopefully, we will be actually having more of those challenges solved.
Yeah, and I have the impression also because I mean, in computer vision, like deep learning or networks have been the way to really be able to have some semantic information on the data. And the fact to have some semantic information on 3D data also implicitly makes a link between the practical application and what we can do or our job kind of on working on 3D data. Because since it's interpretable, it makes sense to people from the from the outside world, and they can really ask their question in their world and in their like in medicine, or so it's not a canal surface, it's a vessel, and it can be interpreted now by a learning algorithm. So maybe also all this learning and this semantic information will be a good way to bridge between what we do and what is needed kind of in the real world. And that can be a nice way to bring the questions and to use this knowledge that we were talking about that was like kind of insider knowledge before and can be interpreted through the learning algorithm. But data is, as you say, Ilke, data is huge, and and we have been just talking about 3D static data, I think, today. So there is if we make things dynamic, and then poof.
Yeah, we didn't even go to that dimension today, right? Like we were like all thinking about models and static things and not changing, and yeah, and then there's the other one, like if things are actually changing through time, not just moving, but they are like deforming, right? And deforming non-uniformly, and like that's even going to another level. So yeah.
One good thing is that time is continuous.
Or is it? We have frame interpolation techniques that we are doing actually to like super slow-mo and like fast, or like, yeah, you know, we can actually like loop in time or something. Anyway, just joking.
So the question of what it will be in 5 years is a non-differentiable question. Right.
Let's find a differentiable solution then.
So we are going towards the end of the workshop. Anyone has any last words for anything you want to comment about?
By the way, the final question. So I was wondering if there are any works on combining NLP with vision, like, so let's say in our workshop, geometry computing, let's say, okay, I want a polygon with 5 edges. So like then some kind of fancy neural networks can automatically generate a polygon with 5 edges. Is there some kind of relevant work or data set or something we can look at? So because I see like there's an emerging trend in object detection, like combining languages and vision. So I was wondering if you can share some ideas or thoughts on this, or I'm getting mad, just something in the air. So
from the silence itself, it is obvious that there's no such data set as of now, but I completely agree. This is more like a, as you know, probably like studied in the context of like scene understanding, and sometimes there is like 3D object detection that you can do, that some semantic object detection, but not on this generative space that you like, maybe in the image space, but not in the 3D space as of now, I would say, especially not in the shape space. In scene space, it's like more like there are scene graphs and you can generate scene graphs, etc. And you can fit some geometry to scene graphs, and that's a little bit easier. But on the shape space, not that we know of, I guess.
Although it is, I mean, it's one small thing to note is just that the NLP space is an area where, you know, you have fundamentally non-differentiable problems that have had a lot of success in terms of the state of the art. So it might be that, you know, I don't think this was exactly the question that was asked, which is using NLP to control geometry tools. But I do think there's some room to draw some inspiration from that literature and maybe translate some of their ideas to this area. So we'll see.
Sorry, can you explain like the NLP is non-differentiable in terms of what, in which perspective?
Sure. What's the derivative of a word? I have no idea. I mean, there are many attempts to embed and do all kinds of interesting things, but you know, fundamentally, these are discrete combinations of letters and so on. You know, grammar itself is a bunch of combinatorial rules, and
okay. Another thing pops in my mind is order, like order of sequence, the words. That's also non-differentiable.
That's right. So it's a great example of a space where learning has been extremely successful, and it's not clear where the derivatives are. So maybe we should be
pixels are differentiable. Like pixels are also ordered in a certain way. Until we have greetings, edges, but there must be something in languages or not.
Okay, well, we'll have to keep thinking about that one. There are a lot of interesting challenges here.
Oh, sorry, I have too much beer, so.
No such thing.
Okay, I really like the conversation. Yeah, no such thing. I personally want to thank all the organizers. I will go in the order of the Zoom: Adarsh, Geraldine, Dana, Bernard, Aditya being in the committee, Sebastian, and I would like to thank all the participants, authors, especially Keynote, staying with us like all the way to the end. And I hope this was useful for you. All the talks will be, so all the spotlights and orals are already in the website. You can just like go download, watch them now. And for the keynotes and these discussions, it will be put in YouTube. We have been streaming the whole day. We will probably cut it into like parts instead of like putting a full day workshop. We will cut it into parts of talks, etc., and put it in YouTube. You will see it in the workshop too. Yes, yeah. Some of the committee members are not here because of the time differences. For example, Alexei, thanks for solving the streaming issue last minute. Bernard for like being there to help us every critical time that they are there. Catherine, she's not here, but like doing all the last minute reviews and like always being there to guide us. So yeah, thanks everyone for joining. And hopefully we will see you in CVPR 2022 in the 4th edition of Deep Learning for Geometric Computing workshop.
Yes, thank you. Yeah. Thank you for the excellent show.
Thanks,
Best
everyone.
paper. You make my weekend.
Thank you. So go computing, Skeleton, and ABC. Go download the data sets. Everything is in Kodalab. Thank you.
Thank you.